Okay, I see that it's the top of the hour, so I will get started. Good morning, good afternoon, good evening. My name is Sam Datta. I'm one of the program organizing chairs, and welcome to IPPW 2021 Session 3. I wanted to go over some rules and some information before I hand it over to the session chairs. First, all the content that will be presented today is getting archived, and it will be available on the IPPW website, the archive site, within a week. If you go there now, you will see the content for session 1 and session 2 already available. The session is also getting recorded, so the recording will also be available on the archive site. Once again, session 1 and session 2's video recording is already available. And finally, as I mentioned to a few of you already, that please do not unmute yourself and talk if you're not the speaker. We will be moderating and making sure that people don't unmute themselves if they're not the speakers, but please try to refrain from doing that yourself. And with that, I'm going to hand it over to Al.
Hello, everyone. My name is Al Wachowski, and it's my pleasure to introduce our ALSEEF award-winning keynote speaker. Ms. Michelle Monk has served as NASA's Entry, Descent, and Landing Systems Capability Leader since May of 2017, and the Principal Technologist for EDL Technologies within NASA's Space Technology Mission Directorate, STMD, since 2013. Undetailed at NASA HQ, Ms. Monk is responsible for ensuring sustainment of NASA's EDL skills, facilities, and tools, as well as guiding STMD's technical content in EDL. Portfolio investments include inflatable decelerator, yay, parachutes, heat shield, precision landing, ground and flight tests, plume surface interaction modeling, aeroshell instrumentation efforts. Ms. Monk's duties include advocating for new investments to close technology gaps and coordinating closely across all STMD programs and technology readiness levels, including commercial and academic activities, as well as with robotic and human exploration, planning, formulation, and review efforts. Ms. Monk has over 30 years' experience in orbital mechanics, trajectory simulation, flight hardware development, and technology management from 4 different NASA centers. She's currently the principal investigator for 2 stereo cameras on the Lunar Plume Surface Studies, SCALPS, payloads. Her past work includes 9 years as lead engineer and project manager for in-space propulsion technology, Aero Capture Project, deputy project manager and subsystem lead for Mars Science Laboratory, EDL, Instrumentation, Medley, flight payload. Ms. Monk holds a BS in aerospace engineering from Virginia Tech, started her career as a cooperative education student at the Johnson Space Center. She's an AIAA Associate Fellow and has several publications in NASA Group and Individual Achievement Awards, including Space Flight Awareness Award, NASA Exceptional Service Medal, and the 2020 ALSEEF Award from IPPW. Fun fact, Michelle did a To Mars and Back Meet Women Breaking Barriers in NASA Langley in March of 2021, and in that article, there is a picture from Michelle from 33 years ago. I don't have authority to project here, but I urge you all to take a look at a very young Michelle Monk. Take it away, Michelle.
Wow, thanks, Al. That was wonderful and scary all at the same time. Thank you all for attending the session today. As everyone has said, for these sessions, I really wish we could be in person, and I look forward to next year, hopefully when we can be back together. Today, I think I have only 30 minutes to cover 33 years, so had to focus quite a bit, and I put together something that's a hybrid between a little bit of look at my career and also the origins of our entry, descent, and landing community. I think we're a really special community, and sometimes people ask me, why are you so different? And so I want to give you a little bit of perspective on that today, as well as show you some of the origins of some of the things that you see in our current portfolio and mission set. So with that, we'll get started. Next slide, please, Tim. Okay, so a little outline, talk about my experience and actually what I just told you. So let's go on to the next slide. So as Al described, I started as a cooperative education student in 1987 at Johnson Space Center. And along my little timeline here, taking us to the present, I've put some of my little milestones. And so from 1987 to 98, I was at Johnson Space Center, and really this is where I got my technical start. I was working on the human Mars mission with interplanetary trajectories. We did lots of other things like human lunar missions. I got my first taste of flight hardware with something on the International Space Station called the moding indicator, which hooked into the GNMC system. And we did lots of studies of vehicles that never made it past paper. So I must have made an impression because in 1998 there was a shift. There were too many people at the operations centers and too few people at the research centers. And so Bobby Braun and Dick Powell came to JSC from Langley and recruited me because they knew I was from the East Coast and so was my husband, and so they thought I might be willing to move to Langley. It was a very tough decision, but ultimately I decided that I could probably go work on robotic missions and still work on human missions later, and that's exactly how it's turned out. So at Langley, I started doing analysis for the Mars Sample Return Mars Ascent vehicle. We also started the Aero Assist working group during that time period, and I'm going to talk more about that. I was on the operations team for Mars Odyssey aerobraking, which was really exciting and very nerve-wracking at the same time, but a great experience. And I also made a move over to a program office during that time and stepped into some technology leadership. I was actually at an Aero Assist working group meeting and talked to someone on a plane on the way back, and a few months later I got a call from Bonnie James at Marshall Space Flight Center asking me if I wanted to come down to Marshall in 2002. And so if you want to click one more time, Tim, thank you. It was a one-year detail, and they needed a lead engineer for an aero capture project. Well, of course, I jumped at the chance for that. And so I became the lead engineer. It was a technology program funded by Science Mission Directorate. And I learned how to write contracts and how to lead technology development. But at the same time, I learned a ton about aerothermodynamics and TPS and aeroshell structures. During that time period in 2006, we put together the New Millennium Program ST9 Aero Capture proposal, and I was the principal investigator. It's a really rewarding experience, even though we didn't win. And the agency was embarking on yet another road mapping activity called Human Planetary Landing System. So we got to work with JPL and all of our partner centers on that. So my one-year detail, you'll notice, did not end in a year. I did not have a good escape plan. But in 2007, my contracts were kind of over, and the program office moved to Glenn Research Center. So I came back to Langley, and I jumped right into Medley as the subsystem lead for the pressure system and the deputy project manager. So, of course, that took us until 2012 when that was successfully entered on the Mars Science Laboratory, and we got our great data back. So that took a huge chunk of time, and I learned a lot about more flight hardware. We also did some other activities during that time period, including the EDL systems analysis and formal agency road mapping in 2010. We also had investments in aeronautics, in hypersonics, and in HEO in the EDL technology demonstration project, and I was involved in those. And then in 2013, someone's got an open microphone. In 2013, as Al said, I became the principal technologist for a Space Technology Mission Directorate, and in 2017, the systems capability lead, which just kind of added to my responsibilities in stewarding our community. During this time period, we worked on getting the NASA Engineering Science Investigation Policy into place. And most recently, I saw a gap and wrote a proposal and became a PI for a science payload on a lunar mission, actually 2 lunar missions. Really whirlwind tour, but the things in red here are the things that I'm going to focus on in the next several slides. So next slide, please, Tim. So how did this whole EDL community actually get started? I'm sure there might be some other stories about it and different perspectives, but I can only give you mine. So as I said, at JSC, we were leading the Human Mars mission architecture studies, and we did that for several years in different 90-day studies and such, design reference missions. In my role on designing the interplanetary trajectory, we then went into, what do those choices of the trajectory and other ground rules like the crew size and how you want to limit the transfer times, how do those translate into the entry vehicle that you need? And so that really all tied together into designing this aeroshell, which we called the trans-hab aero brake at the time, or the ellipse sled as some people refer to it still. That yellow thing on the right-hand picture that was literally drawn on the napkin that became sort of the aeroshell for our transit habitat for taking the crew to Mars. JSC needed some additional expertise in aerodynamics, aerothermodynamic structures, and TPS, and of course they turned to the research centers, Ames and Langley, for that expertise. And, I didn't go into a lot of detail, but imagine going to work and not having a cell phone, not having email, not being able to Google things, just having a desk phone and some conference rooms with telephones in the center, speakerphones. That's the environment we lived in, and so there wasn't a whole lot of collaboration unless it was necessitated by something in particular. And so this was really what I saw as the driving force behind the origins of our collaboration across the agency. Next slide. And then, as I said, in 2001, when I got to Langley, we kind of kept this group together, and we were asked to form the Aero Assist Working Group. And I won't read the whole thing to you, but this was our charter to provide leadership for agency activities and technologies for Aero Assist, drawing on expertise and providing advice and recommendations to NASA programs, projects, and mission directorates. And these functions are very close to the system capability leadership development role that I have today. Next slide. A little more detail on our charter. I'll just pick out some other words for you here. We'll have this, in the archive for the record, but, integrate Aero Assist efforts across the mission directorate, support ongoing mission activities, develop approaches to integrate future missions and how they do Aero Assist, look at high priority technologies and define what those top things are that we should be investing in. And then drawing members from the NASA field centers to include all the areas of expertise. And if you read this description, it's very much like an early system capability leadership team that we're operating today. Next slide. So as I got to Marshall with this community kind of already formulated, they didn't have a whole lot of funding. I think we got $1 million 1 year from what was then called Code R to start looking at some of those priority technologies. But SMD really gave us the kickstart that we needed. And so I show you this chart, not to go through all of it, but to show you that there was a prioritization process with many different types of propulsion technologies considered and bounced against those mission requirements that we could see from the future for that were put out there from the solar system exploration vision and road mapping. We did some system concepts and then prioritized those technologies that would have the biggest impact on those future SMD missions. And you see the matrix at the bottom of the page, high priority, medium, low, and then high risk, high payoff. And, aero capture was considered a propellantless propulsion technology, which is why we were considered in this portfolio, along with, ion propulsion and solar sails and advanced chemical propulsion. So we're really lucky to be included in this technology effort. Next slide, please. So as lead engineer, when I got to Marshall, we started by polling the community and seeing what was of interest and of greatest challenge to the technical community. And so you see some of the things on the left that were the challenges that we identified, technology, test facilities, instrumentation, simulations, uncertainty in the environment, all the things that we would probably say today. And then we took those and looked at the different technology development activities that could be done and how those might all come together into ground testing, a flight demonstration of aero capture, and then with the goal being mission implementation, of course. At the same time, we were looking at rigid structures and thermal protection systems. We also had our eye on balloons and inflatables as more advanced methods of implementing aero capture. Next slide, please. So here was our technology development strategy, very much like what we try to do today. We had lots of science missions to Titan, Neptune, Venus, and Mars on the priority list for SMD, and we took those and did more in-depth system analysis on what the aero capture system would look like for each of those. That allowed us to then identify gaps between the state of the art and what the performance needed to be for those missions. We took that combined with the community input that I showed you on the previous page, and we put out solicitations for subsystem and system development. SMD was largely driven, as it is today, by competition, and so we did competitively select those awards. We then had plans to integrate that system and validate it and, execute the feedback loop for model validation, which was very important to us, of course, and then also infuse this to the first use customer. Next slide. And so in that important box of systems analysis, we did 4 studies, actually 5, if you count our New Millennium proposal. And we looked in depth at Titan aero capture, Neptune, Venus, and Mars sample return orbiter aero capture because it was high mass. And these were all really establishing the state of the art in aero capture, and we were very diligent about publishing the results of those. And I'm sure anybody who's working in aero capture today has probably looked at those NASA technical memorandums or conference papers, but I feel like this is one accomplishment that I'm really proud of, that we put this body of work out there for everybody to use. Next slide. This was our competed content. As I mentioned, we actually awarded 2 task agreements to 3 to AIMS for TPS and aerothermal analysis, to Langley for high temperature structures, and then also to AIMS and a company called Elaret at the time for sensor development. And we also awarded 2 contracts, one for thermal protection systems to Applied Research Associates, and then to Lockheed Martin for carbon-carbon hot structure aeroshell, in addition to improvements on their SLA system. Next slide. So I'm going to show you just some really just eye candy from each of these, because some of these efforts really produced the results and the foundation of what we're doing today. So think, this was between 2003 and 2007 is when all of this work was executed. So at Ames, we funded a mercury xenon lamp that tested at the right wavelength for the CN radiation at Titan. We did shock tube testing and ballistic range testing, arc jet testing, as well as modeling. And so these are the roots, really, of the entry systems modeling project that we have today. Next slide. At Applied Research Associates, they were looking at a ablator family. So they had a carbon-based, carbon phenolic family of ablators, as well as a silicone-based. And they would vary the density of those to meet different mission applications, which is a really forward-looking idea. We did arc jet testing and manufacturing. We went from coupon level up to panel, and we tested at the solar tower out at Albuquerque at Sandia National Labs, which is a really unique facility that focuses about 220 mirrors on a spot on that concrete tower in the lower left there, and gives you a pretty good heat flux. And so that the other significant thing that happened was that ARA really designed a modular heat shield, because the idea of gunning thermal protection system into a honeycomb was really not good from a timing and schedule manufacturing perspective. And so that was really, I think, the roots of the idea of using a block or modular thermal protection system, which of course we're doing on almost all of our vehicles in the forebody today. Next slide. And just one other note on the Sandia Tower testing. This is a fantastic photograph taken by Steve Moon, who was supporting our project at the time. It's dark because of the filter on the camera. That's a 1 meter aeroshell that's being subjected to about 150 watts per square centimeter at the solar tower. And you can just see the pyrolysis products ribboning off from the test. And so that photograph actually won an award from the Aviation Week. And I just wanted to pause a moment and pay tribute to Bill Congdon of Applied Research Associates. We lost Bill earlier this year, but he was definitely a pioneer and a fantastic chemist and engineer that we really enjoyed working with him throughout this time period. Next slide, please. At Lockheed Martin, as I mentioned, we worked on a carbon-carbon aeroshell development, and so they made a 2 meter carbon-carbon hot structure with an insulating material inside. It was actually rib stiffened and coated, and they tested it just like they tested the aeroshell for Mars exploration rovers. And this technology is now being infused on Da Vinci Plus, the recently awarded Discovery mission to Venus. Next slide. And then we had some balloon investments. Ball Aerospace was looking at what they call a clamp balloon, which is that big one on the left where the spacecraft is in the front, and that large toroidal structure was in the back. They also looked at a towed balloon, and so this was a drag modulated system where that torus was inflatable and was so large that it actually saw continuum flow, whereas the spacecraft would continue to see rarefied flow, so it wouldn't need much thermal protection system on it at all. They did some really unique testing on that concept. So you can see where some of these ideas for drag modulation and toroids actually started out. Lockheed Martin was also looking at an inflatable aeroshell concept where they had those ribs that you can see on the right-hand side in the back were the ribs actually intersected and they were inflatable, and learned that that was not such a good feasible design, but that was a valuable thing to learn for the future of the balloon efforts that we see today. Next slide. So now I'll turn my attention to kind of the story for instrumentation. So we were all struggling as a community with getting flight data, and I had been working with others on instrumentation efforts. You've kind of seen that word on several slides now, and assessments and historical looks since about 2001. So finally, in 2006, it took Mike Griffin, who was our administrator at the time, to say in a speech to the National Space Society, we missed a great opportunity by not instrumenting Genesis and Stardust. And so at the end, he said, think about the kinds of synergies that we can achieve if we can obtain on our next Mars missions a better characterization of its atmosphere. And so that was really kind of the kickstart that we needed to be able to implement Medley on the Mars Science Laboratory. Next slide. So we were added to the mission after Aeroshell preliminary design review. So we were constantly in catch-up mode, but of course you all know the end of the story. We were very successful with our 7 pressure ports and seven integrated thermal plugs with data gathered by our sensor support electronics, and really demonstrated a great data set and advanced our state-of-the-art for Mars aeroshell instrumentation. Next slide. And so I have my Medley 2 shirt on today. So we improved upon Medley. We stayed within the same channel count and the same rough cost limit, but we were able, with our experience from Medley, to implement lessons learned to put in even more instrumented plugs on the heat shield to get broader coverage, and to add significant amount of instrumentation to the back shell. And so you'll be hearing lots about that during IPPW. Next slide. So as of 2014, we were still gathering information and putting together information about instrumentation on entry vehicles. And this is one picture of that. So we have the TPS mass fraction and the heat load, but all the previous missions that had done planetary entries, and the size of the bubbles just indicates sort of the size of the vehicle, and they're all color-coded as to the destination. But what you'll notice here is that only the most expensive missions were being instrumented, and the smaller ones like MER and Phoenix and Stardust and Genesis had not been instrumented. So we really wanted to work on correcting that, because we didn't want to instrument just flagship missions like MSL. Next slide. So I and others, I was not solely responsible, but I kind of had the lead on making a request to the NASA Technology Executive Council in April of 2014. And basically what this says is we want NASA to consider instrumenting every entry vehicle. We want the mission directorates to work together and fund that instrumentation. And so this led to the AO requirement that we have now in every SMD, Discovery and New Frontiers AO, to instrument entry vehicles, and that's what we call Engineering Science Investigation, or ESI. Next slide. And so it took us a while to get a winning EDL proposal in New Frontiers and Discovery, but we did it. And so on New Frontiers 4, of course, we now have Dragonfly, which has the DREAM instrumentation package on it, so we're very excited about that. And then the 2 recently selected Discovery missions to Venus, Da Vinci and Veritas, will also have Engineering Science Investigations. So we're really looking forward to getting that flight data. Next slide. So I have a few closing thoughts. Technology development and fusion takes a long time, and it's influenced by factors outside of individual control. You see that, we worked for years on instrumentation and advocacy and everything, but, it took the administrator to do that. However, we as individuals make all the difference. If we didn't exist and we didn't carry our message and we did not have the data and do the hard work, none of these things would happen. And I would just say to remember that, patience and maybe it's just perseverance frequently pays off. Even canceled projects and abandoned efforts are training tools. I know they're disappointing at the time, like the New Millennium ST9 proposal. Losing that was just devastating. But, I learned how to write a good proposal. I learned how to take 12 pages and pare it down to 3. And so that helped me get my Scouts payload awarded. But, really important to document and share findings and lessons learned, because that's how we all grow, and we can grow so much faster if we do that service to one another. And remember that sometimes an idea doesn't need to be trashed. It just needs to be shelved for a while. So, I've met several folks over the past year or two who are working on error capture. Error capture is cool again. So hopefully we'll see the threads of all the foundation really come to fruition. I would say to remember to base technology investments on solid technical data. Those systems analysis studies that we did in 2002 through 2006 were really instrumental and really made me feel like I had integrity when I was advocating for investments. And the same is true today. I think we need to do a better job of really getting the EDL community engaged in mission studies so that we have a firm basis for the work that we need to do to advance our state of the art. Next. Use all the tools at your disposal to advance the state of the art. I didn't talk about this a lot today, but if you ever hear me talk about my job in Space Technology Mission Directorate, that's really what it's all about, is using small businesses and universities and competed and directed work all together, not just saying, well, they're not giving me money to do what I want, so we can't make progress. And then finally, be willing to listen, to learn, and to even go live elsewhere. It is so instructive to learn different perspectives and different cultures, but it really builds your network and allows you to be an advocate and for people to put their trust in you. So that would be kind of my overarching statement. Always be willing to listen, learn, and open up. And finally, my last slide, I really want to thank the ALCEF Award Committee and IPPW International Organizing Committee for bestowing the ALCEF Award upon me. It's very humbling, and just thank you, and I really appreciate it.
Well, thank you very much, Michelle. That was a wonderful presentation. So far, we have one question from Al Castle. Can you describe the entry system instrumentation approach for Da Vinci and Veritas?
Well, I think I'm not going to give you too many details because those are really still being worked out, and their proposal information, of course, is proprietary, but I would say that Da Vinci is planning some PTO instrumentation on their entry probe, which is very exciting. And for Veritas, since it's an aero braking mission, it won't have as much direct instrumentation, but there's a very comprehensive effort to take the aerothermal and aerodynamic analysis along with the aero braking flight data and to advance our models and atmospheric predictions. So I'm sure we'll be hearing more about that as those missions get into implementation.
You didn't go into detail on what's on Dragonfly. How about some more detail on what's on Dragonfly?
Gosh, I am going to I'm going to defer that. I'm sure there's a talk about that soon in one of the IPPW sessions. Maybe today.
Actually, there is. There is
Okay.
at 11:30.
Yeah,
Yeah,
so
Sorry about that.
this is Aaron. We have Aaron Brandis
yeah, so I'm going to let
later in the session.
tell you about that. Yep.
Cool. Anyways, my next question. Wait a minute. Here's one from Samuel Albert. You've been a part of many technology roadmap efforts, and things don't always go as planned. Can you speak to how these influence the community? The unselected proposals. How do they influence the community?
That's a great question, Sam. That was to my, persevere, but sometimes you need to move on. And I moved on after ST9 error capture proposal because a lot of political things were happening and people were in roles that it was clear that it wasn't going to happen on a science mission in the next several years. So I turned my attention to other things. But, as I said, document as you can and, share those lessons learned. I think we're doing a really good job amongst ourselves of capturing lessons learned and sharing those with each other, like on our instrumentation suites. The Dream team and the Medley team have shared. And so, how does it influence the community? I think, sometimes as you saw with error capture in 2006, you see a lull in publications, and you see us kind of take a pause and back away sometimes from some things. And it's really another aspect of technology development is really being able to kind of read the room or read the community. And so, and the community is changing. I would say the space community is changing a whole lot more rapidly now than it used to. So having your eye on what's going on in the commercial industry is even more important now than it has been. But it's really interesting. They're driven by different things, and I think just continuing to do those assessments of, is it the right time for something might, serve us well.
I have a question for you. What is the next big thing that we're going to see? You've been working on, for instance, aero capture for quite a long time, and inflatable heat shields and all those sorts of things, and supersonic retropropulsion. What's the next thing we're going to see that's going to be on the mission?
Ooh, I don't have a crystal ball. I wish I did, but I'm really
your best guess.
Yeah, I'm really excited about inflatable aeroshels, of course. I think the lofted 6-meter demonstration is going to really open a lot of eyes, and we're going to, we have a lot of commercial interest in those inflatables for asset return. So, if that takes off, I see that as really expanding and sustaining the vendor base so that could be a more ubiquitous solution for entry missions leading up to humans at Mars. I also see lots of promise for small spacecraft, and I'm really intrigued by the cost being the objective function of an entry system, and how can we make cheaper entry systems that meet the commercial needs and really allow us to expand our reach. We've still never done a network of landers, and so, or a network of orbiters that could, give you a constellation of navigation at another planet. So I think all of that is really on the horizon for us.
Wonderful. I think this will be the last question. It's from Robert, and I'm going to butcher his last name, Okoji. Anyways, Robert asks, what is the optimum number of sensors needed to instrument TPS, and is distributed sensing important?
Very good question, Robert. I would have to say that the optimum number of sensors really depends on the size of the vehicle and the flight environment, what kinds of phenomenon you're looking at. Are you looking at transition to turbulence, or what's your biggest unknown, I guess, that you're going after? So On March 2020, from our experience on MSO, we decided to distribute those thermal measurements across a wider area and to really get more information about that transition zone and how the front progresses, as well as, some of the heating out near the shoulders and things that we couldn't really capture with the first medley. So I'd say it depends, really figuring out what is the uncertainty that you most want to drive down, and focusing your instrumentation on that area is the approach that we've taken so far.
Okay, we're out of time for Michelle. If you have further questions, perhaps Michelle will be able to hang around for a little bit and respond to you directly in the chat. And I'm going to, I believe, hand it away to Alan Castle.
Yes, and thank you, Al and Michelle, for that wonderful keynote address. So on behalf of the EDL Technology, Science, and Instrumentation session conveners, Julie Kowalski, Aaron Stahura, Tom West, Al Witkowski, and myself, I'd like to welcome you to the oral presentation portion of the program. For the first half of the oral presentations, I will introduce the speakers and keep time, and Tom West will moderate questions and answers from the chat. So please, speakers, please note that I will announce a 3-minute warning prior to your scheduled end of the speaking slot. So first up today, we have Carolina Restrepo. She is an aerospace engineer at NASA's Goddard Space Flight Center in the Navigation and Mission Design branch. She has been involved in technology development projects for precision landing at the Johnson Space Center and the Jet Propulsion Lab prior to joining Goddard Space Flight Center, and is now working with the team on developing map products for lunar navigation and hazard detection applications. So please take it away, Carolina.
Thanks, Alan. Can you guys hear me okay?
Sure can.
Okay. All right. Well, hi, everyone. Like Al said, I'm Carolina. I work at the Navigation Mission Design branch at Goddard. And before I get started, I want to acknowledge my co-authors. We have a good portion of the LRO science team at Goddard on this project. And then we have JPL team members as well as AIMS. Today I want to talk about a relatively new effort that we are taking on as of last fall to try and build maps for navigation applications. Historically, a lot of the map products have been built for scientific applications, but we've realized recently, or somewhat recently, that having the right maps for things like terrain relative navigation or hazard detection takes a very specific effort. And so we are trying to work on developing not just benchmark data sets, but also tools and guidelines for how a team can come up with their own TRN maps for the upcoming lunar missions. Okay, next slide, please. So this might be stating the obvious here, but I just wanted to go over why we need maps for precision landing. If you want to click through the whole sequence in the slide, that'd probably be helpful. I think one more, yeah, that's it. So why do we need maps for precision landing? We are expecting that most landers to the moon will have some sort of terrain relative navigation on board. And for the purpose of this presentation, we are going to assume that the terrain relative navigation system has a reference map. So we would be navigating with respect to a reference map. Now, this reference map would be created ahead of time, and it needs to be as close to the truth as possible and derived from orbital imagery. So the TRN systems would use this reference map to locate the spacecraft with respect to that reference map. These reference maps don't include small hazards like small rocks or craters that are maybe centimeter scale that could still damage your lander. So hazard detection systems, if a lander is equipped with a hazard detection system, that is, they would need to detect hazards that are much smaller than what can be seen from the orbital imagery. So hazard detection systems would need to generate a new map when we're closer to the surface that is much higher resolution than the maps used for navigation. Hazard avoidance systems would then use those maps to avoid hazards. And we would still need additional onboard sensors to perform a soft and controlled touchdown at a safe site. So next slide, please. I think a couple more times, 2 or 3. One more. One more, please. So as part of what Michelle talked about earlier, NASA has been working on precision landing technology development projects, and several projects have addressed TRN system development and hazard detection system development. But one missing piece to make TRN successful and hazard detection successful is to have good lunar maps. They need to be accurate maps for TRN so that we can localize the spacecraft as accurately as possible, and they need to be representative maps to develop and test hazard detection systems. So all 3 things, precise landing, safe landing, and control landing, make up the precision landing and hazard avoidance domain. And we are trying to fill one gap that's still needed, and that's navigation maps for the moon. So next, please. So again, in the context of this presentation, we are talking about TRN with respect to a reference map. So the spacecraft position estimates are only as good as that reference map. The descent imagery from the lander takes 2D camera images. Those images are processed and compared to that reference map and matched. And the match can be done a number of different ways. But once there's a match, you're able to derive the spacecraft position and altitude with respect to that reference map. Okay, next slide. So what do we mean by a reference map? So the reference map is really a rendered image of a 3D map or a 3D digital elevation model under the illumination conditions of the day of flight with the right surface properties so that we can match the images that day. The map is also tied to a fixed coordinate system that can be used by the spacecraft navigation filter. So the map won't be, it'll be as close as possible to the truth, but it'll still have some errors, and it'll probably have some bad or missing pixels that need to be taken into account by TRN algorithms. And different TRN systems will have different issues with different types of errors. So what we're trying to do here is come up with maps and processes that are somewhat TRN algorithm agnostic so that we can help the community obtain the right map products for their own systems. Next, please. There are some unique challenges to the moon that were not there for Mars 2020 or OSIRIS-REx, which are the 2 light missions that we've seen recently that did TRN successfully. The moon has a wealth of imagery available, but despite the amount of imagery, it still can be challenging to parse through it and to really obtain all the necessary information to build a reference map for a given site. Merging the data sources, topography images, stereo images, is not necessarily automated. It takes a lot of expertise to be able to handle those tools. A lot of the imagery metadata must be available and understood. The TRN systems need to have good information on what the errors on the maps and images are. It's not easy to validate and verify that we can trust these maps. It's important to define and understand the effects of specific map errors on TRN performance, and it's generally a challenging imaging environment because of the constantly changing illumination conditions, especially at the South Pole, which is one of the things we want to tackle first. Next slide, please. So right now, the sources of lunar imagery and topography that are available to us are the Lunar Reconnaissance Orbiter Laser Altimeter, or LOLA. And LOLA collects topography data. I'll talk a little bit more in the next few slides. But the image on the bottom left is an example of LOLA topography at the South Pole. The LRO cameras also collect images and stereo pairs as you can see in the picture on the right. The image on the middle is a mosaic made up of NAC images, but you can see that there's missing data, there's gaps, there's seams, and all of these things are going to affect TRN solutions if they're present in the reference maps. We also have available imagery from the Kaguya terrain camera, and most recently there are images from India and China that have been made publicly available. So our team is likely going to see if we can leverage any of those for this effort as well. Next, please. So like I said, we have a small project. We labeled it, called it Lunar Navigation Maps, and our objectives are to work on developing maps specifically for TRN and hazard detection, as well as to create benchmark data sets so that we can share those with the community. We are hoping to work on a South Pole site first, and then maybe one or two additional sites so that we can validate our process and share the data so that we can use them to develop algorithms and compare one system versus another system with the same set of standard maps. We also want to assess current terrain rendering capabilities, or at least what it is that we need in the terrain rendering software in order to V&V TRN and hazard detection for lunar applications. Next, please. So our plan, we just wanted to share a little bit of what our plan will be to let people know we are tackling this problem right now. So the first step is to look at the LOLA topography data at the South Pole. Right now, the data is 5 meters per pixel, and part of the LRO science team at Goddard has come up with a method to clean those 5 meter per pixel dams. So they're still 5 meters per pixel, but they have they're much cleaner. They've reduced a lot of the artifacts. So starting with those new clean LOLA dams for specific sites, the other two tasks will gather additional imagery from LROC NAC cameras in Kaguya and overlay them on the dams to create new digital elevation maps of a higher resolution, down to 1 to 2.5 meters per pixel. So
3-minute warning.
Okay. The team at Ames has the Ames Sphere Pipeline, and JPL has a suite of tools derived from the Mars 2020 effort. So we plan on doing things in parallel and comparing the results. Next slide, please. So this is a little bit of background on the LOLA data. This is an example of the track, and the 5 meter circles are basically the LOLA topography data that's collected. Next slide. So when there's a LOLA dam that's 5 meter per pixel, not all the pixels are true pixels. A lot of the data is interpolated, and you can go to the site here to better understand how these maps are built. Next slide. So here's an example of the improved LOLA dams. You can see the maps on the left have a lot of artifacts, like tracks almost, and the maps on the right are much cleaner. Next slide. This shows the sites that have already been cleaned up of the South Pole, and we're working on expanding this pipeline to cover more of the South Pole. Next slide. So the Ames Sphere Pipeline is it's a tool that uses NAC imagery and topography combined to build the higher resolution dams. So it has a two-step process, and I think I have that on the next slide. So it uses a stereo terrain model using stereo image pairs from NAC and then photoclinometry or shape from shading to finish the process and create these 1 meter per pixel digital elevation maps. Next slide. You can click through all the bullets. I think that's it. So we have a plan to V&V some of the map products, but mainly we hope to collaborate with several groups to test our methods and take out a lot of the errors before we can release some of these benchmark data sets. Next slide. And hazard detection requires maps that are high resolution, so we can't see that from orbit, and the plan is to at synthetically generated data. So if you go to the next slide really quick, we have representative maps for HD rather than true maps. So the way we're planning on doing this is by using terrain generation software, but also collecting field data from lunar analog sites on Earth. And we are going to analyze all of the field data and try to improve the model for generating synthetic terrain based on those parameters. So we can generate representative maps for testing hazard detection systems for specific regions at the moon. Next slide. So again, we have 3 separate tasks so that we can have the opportunity to validate our results and allow us to derive metrics for what we call a good map versus a not so good map. And we'll run these through entry-descent landing simulations, both for TRN and hazard detection. Next slide, please. This is just a quick example of some of the field data that the team has been collecting. The image on the left, image A, is a NAC image from the moon, and then image C is data collected from a similar type of terrain on Earth. So we hope to use some of this data to improve the quality of the representative hazard detection maps as part of the benchmark data set we'll be producing. Next slide. So again, our plan is to tackle the South Pole first to try and help the Artemis human landing system landing sites studies, and we'll also pick an additional 1 to 2 sites to try and test some of these methods that we're developing. And we think that working with separate pipelines will allow us to validate some of the map products for wider community use. Next slide. So that's all I have. Sorry, the hazard detection piece was a little bit rushed, but in essence, we just wanted to make people aware that we're working on this. We realized that building TRN maps is not easy if you don't have geologists on board on your team, and so we're trying to figure out how to leverage their knowledge and have better engineering tools so that the TRN system developers can have access to this when they're developing their TRN systems and hazard detection systems. This is definitely a combined effort between geology and navigation, and so we are working on that, and we're trying to tell the community what we're doing so that we can start to share some of the results soon. But that's all I have.
All right, thanks, Carolina. There is one question in the chat, but I think we need to move on to the next talk.
Okay.
So respond in there.
Yep.
We may have lost Alan. But worries, we'll press on. Okay. All right, Danielle, are you ready?
I'm ready.
Okay, there we go. All right. So our next speaker is Danielle O'Driscoll. Danielle obtained her master's in aeronautical engineering from Imperial College London. After completing a year at the European Space Agency, ESTEC, as a graduate trainee, she returned to Imperial College in 2018 to pursue a PhD. Take it away.
Okay, thank you for the introduction. So today I'm going to talk about our research project at Imperial College London, which is focused around the development of the Hathor spacecraft, a rigid deployable aeroshell used for atmospheric entry. I'm going to tell you about the background of this project, the computational tools that we've used to develop our model, then about the engineering model that we are building, and finally the testing that we'll be carrying out to validate our computational models. Next slide, please. So, as I'm sure most of you know, the purpose of an aeroshell is to thermally protect and decelerate a spacecraft during atmospheric entry, and the motivation for developing large surface area deployable aeroshells for high mass payloads, such as future human missions. So far, all successful missions have flown with aeroshells with fixed rigid geometry, for example, the MSL and 2020 mission. And current deployable concepts include inflatable aeroshells, such as HIADs, and also mechanically deployable aeroshells like ADEPT that deploy like an umbrella. So both of these concepts use flexible thermal protection system materials, usually a woven fabric that will stretch across the structure when fully deployed. And this holds a high advantage because it's lightweight, therefore keeping our overall mass down. However, using a flexible material can have some disadvantages too, especially when it comes to reliable deployment, structural redundancy, and predicting its behavior under a high load environment. There is also the possibility of fiber damage when in the stowed configuration. Next slide, please. So, since this is the case, we have explored a rigid deployable design where we've taken the umbrella concept and rather than having flexible materials stretched between each set of ribs, we have rigid panels made up of a structural and TPS layer. These rigid panels are connected via revolving hinges that emulate origami fold lines. They allow compact stowage and lock into place when the structure is deployed. And this design ties in the advantage of a deployable structure that increases the aerodynamic reference area and also that of a rigid structure with behavior that can be easily predicted and controlled. Next slide, please. So when we set out to design our spacecraft, there were 4 things that we wanted to achieve. The first and one of the most crucial is keeping our descent velocity down. This is achieved by having a low mass to surface area ratio. Next is protecting our spacecraft from atmospheric heating by choosing an appropriate material. Then we need to make sure our structure will survive the atmospheric pressure loading. And finally, we want to deploy reliably so that all the other objectives are fulfilled. And all of these are highly dependent on the geometry and material properties of the spacecraft. So when developing our engineering model, we wanted to make sure all of these values were determined. Next slide, please. So the first step was choosing a reference mission that we could compare to. We chose the Phoenix 2008 Mars mission that has an aeroshell mass of 62 kilograms and diameter of 2.6 meters, since we'll be able to manufacture something of this size. And using the trajectory solver that was developed at Imperial College London, we found that there was about 10% difference for maximum dynamic pressure and also for velocity at the start of the descent phase. And this is attributed to the difference in geometry between Hathor and Phoenix. Here you can see that the Phoenix geometry is smooth and axisymmetric, while Hathor is faceted, meaning that the material between each set of ribs is flat. And also at this point, we selected a number of 8 ribs as a trade-off between aerodynamic performance and mass saving. And next, we focus in on this material between the ribs. Oh yeah, there we go. So when evaluating deployment, we must look at how the material between each set of ribs transforms from the stowed to deployed state. And we can control this by imposing an origami folding pattern, as you see to the right on the deployed material. And depending on the deployment ratio, which is the ratio of the deployed diameter to stowed diameter, this folding pattern will change to ensure the material fits between the ribs. And although these just look like fold lines here, in reality, there will be hinges that are placed between thick, rigid panels. Next slide, please. So both types of geometry have been modeled in MATLAB Simscape, and we have been able to validate the more complex geometry against a 3D printed model that was 40 centimeters in diameter. However, for the 2.6 meter model, a deployment ratio of 2 is chosen, as this would accommodate the science deck on board the Phoenix spacecraft. And we found that full deployment relies heavily on the panel geometry, rib sizing, and hinge placement. But these parameters also depend on the aerothermal performance and the required rigidity of the aeroshell, so must be determined through this analysis first. Next slide, please. For the aerothermal analysis of the aeroshell, we created a MATLAB model that models radiation, convection, conduction, and ablation of faceted heat shields on an entry trajectory. And using this model, we were able to characterize Hathor's TPS layer, which will thermally protect the payload during entry. And this layer needs to be carefully sized to ensure that the bond line temperature remains at a safe level, so below 523 Kelvin, while the aeroshell mass and stowed volume are minimized. And we have tested several TPS materials, both ablative and reusable, and decided on a 14mm layer of the super lightweight ablator, which has been used on several previous Mars missions. And this gives a total weight of 20 kilograms. So here you can see the evolution of the surface temperature and the bond line temperature with time for the trajectory and TPS material and thickness considered. Although the surface temperature reaches 1500 Kelvin at peak heating, the bond line temperature remains below 360 Kelvin at the end of entry, showing that the TPS chosen offers sufficient thermal protection to the payload. Heating considerations also influence the choice of rib geometry. So a wide rib at 35 centimeters has been chosen with a curved upper surface to avoid any sharp corners and discontinuities that would have caused undesirable heating spikes. Next slide, please. So as we moved towards a practical design, it became evident that the original fold pattern would not work with industrial hinges while also ensuring sufficient thermal protection. Because of this, the fold lines are reversed and the panel edges extended beyond the fold lines. Panel 2 is also replaced by a frame for mass saving. And this means there are less seams exposed to the flow and all hinges are placed on the underside of the aeroshell. To accommodate the stowed panels, the ribs must now be at 10 degrees, and this gives a deployment ratio of 1.7 since the stow diameter is now increased. And due to the sensitivity of deployment to panel and hinge geometry, a range of possible hinge placements is found that can only be finalized once the total panel thickness is known. So our next step is to determine the material and thickness of Hattle's structural layer. Next slide, please. After designing the engineering model, we then conducted finite element analysis on the structure. We chose to construct the structural layer out of aluminium honeycomb since it has high stiffness and is lightweight. We applied the maximum dynamic pressure load taken from the trajectory analysis and found that when we had a panel thickness of 10 millimeters, the deflections within the structure were small enough to not affect aerodynamic behavior. We also found that maximum deflections can also be eliminated by latching the panels along their edges. And now that total panel thickness is defined, the optimum hinge location can be determined. So this is found to be when the outer hinges are placed at 7 millimeters beneath the panel surface, meaning that deployment interference is minimized. Next slide, please. So a deployment simulation of our final model can be seen here. And if you press play on the model, you might be able to see it fully deploy. I can see that it gets stuck. But yes, the final mass actually comes down to 96 kilograms, a bit more than our reference mission. And this is really down to the presence of motors, hinges, and deployable ribs. Since we haven't yet investigated how this particular design would scale for a much larger aeroshell diameter, we cannot make a mass fraction comparison to other deployable aeroshell designs at this time. And in the end, the structure still allows significant volume saving within the rocket payload module. Next slide, please. And this is what we have constructed so far. We've put together the main framework and are currently assembling the honeycomb panel layers. And here you can see one set of panels in the stowed and in the deployed configuration. Next slide, please. So we've also been testing the actuation of the system, which will be comprised of 8 sets of motors, each driving a rib. Speed reduction is provided by a worm gear set and 2 stages of timing belts. And the timing belts are to allow simpler construction, and the worm gear is non-backdrivable, providing the first layer of locking. Further locking is provided by the 4-bar mechanism, which drives the rib. In the fully deployed state, 2 bars are collinear and push into place against a hard stop, so the loads on the ribs cannot cause the 4-bar to displace. And as you can see here, we've also tested single panel deployment with just the honeycomb layer in place. And since all motors are connected by a ring of shafts, the motion of the ribs is synchronized before the reduction stages, and this allows the entire system to have redundancy against individual motor failure. Next slide, please. So once our model has been fully constructed, we will be carrying out a number of different experiments that will validate our computational models. We will conduct deployment testing, which will validate kinematics, locking of latches, geometric interference, and actuator performance. Static loading tests will measure structural deflections and maximum dynamic pressure, validating our finite element results. And finally, wind tunnel tests will assess the effectiveness of our inter-panel seal designs. Next slide, please. So to conclude, I've outlined the development, analysis, and design of a rigid deployable aeroshell. We are currently constructing our model with the view to begin testing in the next month. And this will provide insight into the feasibility and scalability of this new rigid deployable aeroshell design. Yes, thank you for listening. I'd be happy to answer any questions.
Excellent progress, Danielle. Do we have any questions, Tom?
Yeah, one just came in. Would it be possible for the deployed panels to be jettisoned during hypersonic flight for a drag modulation aero capture application? And then follow on, what is the ballistic coefficient ratio between the stowed and deployed configurations?
Oh, I must say I don't know that off by heart, the ballistic coefficient one. But yes, it could definitely be jettisoned. The way we've designed it is so that we have a very low truss structure below, so that it definitely can be jettisoned at any point.
Okay. Helen asks, will SLA be applied to the model?
No, SLA won't be applied to this model. We're actually manufacturing our current design out of cork, and this is so that it has a similar density to SLA, but no, we can't get hold of that.
All right, Sam Albert asks, how would you avoid seams or gaps exposed to the flow between the panels?
So the idea is that it deploys very accurately, and that there's a kind of interference when it fully deploys, so it'll kind of lock together. This is something that needs to be tested and will definitely be done in the future.
Okay. And that's all there is.
All right. Thank you, Danielle.
Thank you.
All right. We have Max de Jong up next. So Tim, if you could bring up his presentation. Max is the CEO and Chief Engineer at Thin Red Line Aerospace, a company specializing in soft goods development for manned and robotic space exploration. And if you ever get out to British Columbia, please go by and visit Max. He's got a great shop out there in the beautiful country surrounding Chilliwack, British Columbia. So take it away, Max.
Thanks a lot, Alan, for the flattering introduction. And thanks, everyone, for just listening into this presentation. So this is a very interesting project. Well, they all are for what we're working on, it seems to be. First off, I very much want to thank my co-authors for being partners on this project. Besides being very talented engineers, they are also, over the last year, they've very much become friends of mine, which makes it all the more exciting and fun to continue work on such an interesting project. Next. So I won't go into any real historic data or details on different architectures that have been used for decelerators. I think Michelle provided a really great introduction, and I think everybody's familiar with the concept that for deployable decelerators, there's been I think 5 or 6 decades worth of study that's gone into it. I want to zero in on one of or probably the most basic concept, which is the tension cone that you see on the right-hand panel of this slide, mainly because the current state of the art, like NASA's HIAD and the structure that we're working on, are in a way derivations of this concept, of this elegantly simple concept. Next. The thing with the tension cone is what we need to do is we obviously need to derive a very, very large structural drag profile, so a very, very large diameter. And the easiest way to do that is with an inflatable torus, let's say if it has to be deployable. And then if you have a fabric cone right in the center that can create a conic frontal profile, that constitutes your inflatable structure as a totality of what you need for a deployable decelerator. The only thing with the tension cone is, or the biggest thing with the tension cone is twofold. It's very, very difficult to make a torus that's structural, that'll maintain its shape under a whole variety of flow conditions and loads. And then secondarily, the fabric membrane in between it is obviously like a hammock. It's subjected to all kinds of deflections, distortion, wrinkling, and so on. So you get a large degree of indeterminacy, embedded shock formation, depending on the velocity, especially hypersonic, heating indeterminacy, etc. The NASA folks at Langley, they came up with a solution to all these things. Essentially, they've done a phenomenal job. Of course, we're all familiar with HIAD, and they got rid of, the issue of buckling because, first of all, they know a lot about how to develop a torus that doesn't buckle, but also by stacking them concentrically, it really eliminates a risk of divergence in torus, behavior over a range of flow conditions. And then when it comes to the cupping, because they have a stacked pyramid of tori, it gets rid of that issue of the membrane cupping. We come to this issue from a very different area. We're coming to it from being soft structure specialists on the heels of the Bigelow Aerospace program, where we developed the inflatable habitats. We've always been looking for structural determinacy. So we're looking at perhaps is there some simpler way to do, or another simple alternative to building a decelerator architecture? Next. So our background is coming up with structures that we can predict using subscale models, subscale hardware, that we can predict what something in a 10 meter or 15 meter can, what it would behave like. In other words, we need to have a structurally determinate architecture. And I won't go down that path for explanation because that's a very, very complex issue. But essentially, this is where we're applying our technology that we've developed, this containment technology called UHPV. We're applying it to a decelerator scenario. Next. The matter with UHPV that makes it attractive from a habitat point of view, containment, propellant tanks. We've been working with this architecture for the last 15 years or so, and it's been validated through many, many, many programs. It's probably about the highest specific energy containment architecture that's out there. It outperforms any titanium tanks and so on and so forth. But the biggest benefit in a way besides mass is the scalability and structural determinacy. So we can scale it, predictably scale it using very, very simple analytical methods. When it comes to decelerator applications, we found early on with our partners at CFD Research Corporation that it was also remarkably resistant to deflection. And we put it in a wind tunnel in its virgin form, and it would sort of be self-stabilizing. The tendons are aligned very favorably with the flow direction. Next. So we also introduced a concept. Okay, well, that's very interesting. And we went down another path of developing a sphere cone architecture that modifies the frontal surface in a very simple fashion. And that also rendered very, very favorable results when it came to, drag coefficients that were kind of in the same ballpark as the NASA IRVI, prototypes that Langley developed for HIAD. But then there was an issue in one of our contracts. Well, what if we wanted to have the center body or the vehicle payload to be exposed for communications, easier deployment, and so on and so forth? So we kept scratching our head, and we can go to the next slide. That's where this concept came in. We call it the dual body as opposed to the single body. So we have a large diameter drag footprint that's provided by what we call the annulus, which is that toroidal structure that you see around the perimeter. And that's derived from UHPV. I won't go into the nitty-gritty of how that's done, but again, we're looking at something that is statically determinate and scalable. So it's a tendon-reinforced design. Then when it comes to if we're comparing to a sphere cone, looking at that center membrane area that can cup, we've replaced that with a very low pressure inflatable body, as it were. So it's a conic inflatable structure, a secondary to the annulus. The very interesting thing is that we're looking at pressures of under 30 kPa for actual, earth entry systems, for example, less than 30 kPa for the annulus, which is, let's say, 4 PSI only. And then for the conic volume, analysis is indicating that we can get away with as little as 1 PSI, so somewhere in the 7 kPa range. Next. So this is an initial prototype that we developed last year. It's great having young engineers because they're very much into interesting methods of quality control and so on. But this was a successful prototype, just investigating different manufacturing parameters. How can we, develop the frontal surface that it provides the conic profile that we need, and so on and so forth. Next. This is a real pretty view of the frontal surface of that initial prototype that we developed. It's nice when you get a geometry that looks like it's going to maintain the shape that you intended to have. That's always extremely helpful. Next. So then when it comes to the Efesto project, which is the current project that we're working with our European partners and all the co-authors that were listed on the front page, working together, we came up with a dual body adaptation for Earth entry and for Mars entry. And on the right, you can see the methodology that we're using here is we're going for an architectural minimalism, and we're actually using the dynamic flow that you see top right. We start with this configuration in the top right, that shows the deployment in a vacuum, and as we increase the dynamic flow, it assumes the correct conic profile. The general layout, the incorporation with the AVM, with the European launch vehicle, that's shown in the top left, and the general layout of the inflatable structure, the annulus and the conic volumes, that's in the bottom left. Next. This is one of the views of the prototype that was completed a few months ago. It's currently in Italy, and it's going to be undergoing static deflection testing. So you're looking at the aft end, essentially the bottom, and the ring, the metallic ring that you see in the center, that would be the connection to the AVM, to the center body. So the inflatable structure would not be contacting the center body or the payload. And next. This provides the view of roughly what it would look like deployment in a vacuum. This is, of course, without the aeroshell. This is just the pressure restraint structure. And again, the images on the right show how this would deform, how the cone tendons would tension and work in unison with the cone pressure, the very, very low cone pressure, to assume the correct conic profile for the entry. And next. So next steps, packaging and deployment, of course, is always a real critical issue when it comes to inflatables that are larger than the payload fairing of your launch vehicle. Static deflection testing, which is being set up as we speak by our friends at Sierra. And then we, of course, we have the necessity to perform advanced investigation and characterization of the annulus behavior, sort of like all the stuff that our friends at Langley went through with development of HIAD. Even though we have a scalable structure and we have a great degree of structural determinacy, static determinacy, you still need to, sweat all the details of, okay, what type of variation do we have in stability with application of any conceivable external load. So that's that's a very large next step. Next.
3-minute warning, Max.
Okay, thanks, Alan. I'm wrapping up here. Again, none of these projects are possible to bring to fruition without having the right partners and a very talented team. So I want to, really point out just how important it is here. And this is a list of the organizations that are all collaborating together with us to bring this HIAD version to fruition. And I want to thank them very, very specifically. If you have any other questions about Thin Red Line, we can take a look at the last slide. Thin Red Line Aerospace, we've been around in the aerospace business for about 20 years, and another 20 before that, always specializing in soft structures. So we try to keep our nose out of, anything that requires compressive loads. If it's fabric, film, cordage, tendons, rope, whatever, and it has to be super lightweight, and that's our bag. And we work on a very, very broad variety of projects, but it's all pertaining to space. And thanks very much for listening, and I'd love to answer some questions.
Thank you, Max. Those were some beautiful structures. So I'll turn it over to Tom to moderate the Q&A.
Yeah, we got a few questions here in a couple minutes. So the base material looks like Kevlar. Is it, and have you considered alternate fabrics?
Oh, absolutely. So again, we're working with a very, very tight budget. Fabrics like PBO, Xylon are sort of knee-jerk goes to for that type of temperature range. The problem nowadays is now that it's not used in bulletproof vests, the cost of custom developing, PBO broadcloth, it's kind of pricey.
All right. Aaron asks, do you have a concept for dealing with aft body heating or an idea of what kind of aft body heating your unmodified structure could endure?
The unmodified, I'm not sure exactly what you mean with that, but again, what we're trying to do is a stage-wise development. So we're very aware of, the need for incorporation, most likely a burble fence, architecture, which we've already prototyped. When it comes to the heating analysis, that's something that's also in progress, that but preliminary studies that were done early on by CFD Research, they did a wonderful job on taking a look at that, and the materials were all adapted accordingly. The TPS, of course, isn't included. What I'm showing here is really development of the inflatable structure pressure restraint system. So there was an aeroshell prototype there, and a TPS has been built in Italy has been applied to this structure for the static deflection testing.
Okay. Sounds good. There's a couple more questions in the chat. I think we'll roll to the next one, but thanks.
Yeah, thanks, Max. Okay, Tim, if you can bring up Esser's talk, or Burkhard Esser's talk. Burkhard is a research scientist at DLR Supersonic and Hypersonic Technologies Department, where he has been leading the high enthalpy flow research group. He has been involved in many national and European research activities related to thermal protection system characterization and qualification, and was the coordinator of the European research study Thor, focusing on innovative thermal management concepts for future space vehicles. All right, we're ready for you, Burkhard.
Thank you for the introduction, Al. I hope you can hear me well.
Yes, we can.
Okay, I'm continuing now a bit of Maxime's topics because I'm keeping at the Efesto project and turning to the thermal testing activities of this project on flexible TPS for atmospheric entry. And first of all, I would like to thank my co-authors listed on the right side who contributed a lot to this presentation. So next slide, please. The outline. Well, I will very shortly introduce the Efesto project and its study logic. The main part of my presentation will deal with the thermal testing activities in Efesto, which are related to material characterization and Archer testing of flexible TPS systems. Next slide, please. Efesto is an ongoing research project funded by the European Union. It's targeting to improve the European capabilities with regard to inflatable heat shields with flexible thermal protection. And the main aim is to increase the current TRL level in Europe to a level of 4 to 5, and finally end up with a suggestion for an in-orbit demonstrator which could further improve the European TRL level. Next slide, please. The project is a cooperative research activity combining entities from 4 European countries. We have 3 national research institutes of Italy, Germany, and France, a leading university from Italy, Torino, and 2 companies which are main contributors of the European space and industry. The project itself is a 3-year project which started in 2019. We are now at about 2/3 of the duration, and the project will end mid of 2022. Next slide, please. Here we have a bit the study logic and the work breakdown. In the very beginning, we sat down and discussed deeply on potential applications for inflatable, flexible TPS systems and missions related to that. And this came up with the selection of 2 main applications, one for Earth re-entry and the other one for Martian entry. For the Earth re-entry, we are considering the return of Vega's upper stage AVUM from the orbit to the ground. And for that, we have designed a HIAD with a diameter of roughly 5 meters. For the Martian mission, we are looking at an exploration mission, which should be able to land safely a payload of 2.5 tons at a molar of +3 kilometer. And for that, we are considering a height with a diameter of 9 meters. In the first work packages, 2, 3, and 4, we defined those reference missions and did preliminary and detailed design activities to find the relevant numbers, which are later then transferred to testing activities in work packages 5, 6, and 7. The design phase has been completed, and the testing phases, as you could hear from Max's presentation as well, are ongoing. And after the test results will go into the analysis work package, and with that we will develop and we will check the numerical modeling of the materials and develop hopefully new, more validated models, which then will be applied for the design of a consolidated mission for future in-orbit demonstrator. So within this presentation, I will mainly focus on work package 5 with the thermal testing of the TPS next. And next as well, there are other presentations within the range of IPPW 2021 on the FSO. We had the talk by Maxime just before on the prototype design and development of the inflatable structure. For this topic, there will also be a poster later on today, and on August 10, our project coordinator, Davide Bonetti, will have a talk with a detailed description of the complete project. Next slide. Within the testing activities, we had 3 main objectives. We considered materials procurement in the beginning, and then we have 2 testing objectives, which is the thermal characterization of all considered flexible materials, and we are considering arc-jet tests of the defined layups with flexible TPS. The materials procurement and the thermal characterization have been completed, and with the arc-jet testing, we are considering 2 loops. We had first the screening loop, which has been completed, and then after numerical analysis and model validation, we come back with a final selection of the layups and then have a second arc-jet loop. From the design work packages, we got loads for the arc-jet test activities, mechanical and thermal loads, and from the and with our test results later on, we feed the analysis work packages with the results of the material characterization and with the results of the thermal measurements from the arc-jet test. Next slide, please. The information we got from design was based on the trajectories which were defined for the Earth and the Mars mission. We got values for the maximum heat flux along the trajectory, for the integral heat load and the maximum stagnation pressure. For the arc-jet testing, the main first priority data were the thermal inputs. The mechanical loads in terms of the stagnation pressure were of second priority for the test conditions only. With regard to the heat fluxes, we have a slightly higher heat flux for the Martian mission with a maximum of 650 kilowatts per square meter. For Earth, we have only 500 kilowatts per square meter. With regard to the integral heat load, the situation is the other way around, with higher heat load for Earth and slightly lower heat load for Mars. From the design activities, we got 3 different layups for testing, 2 candidate layups for the Martian mission, and 1 layup for the Earth mission. Each of the layups is consisting of external fabrics layers, then some insulation layers below. And at the bottom, we have again fabrics as a closure of the setup. This multi-layer setup we tested in two different configurations. The stagnation configuration will mainly apply thermal loads only. In the tangential flow configuration, we have, in addition to the thermal loading, also some shear loading to the surface. Next slide, please. Before starting to the arc jet testing, we went to the material characterization, and this was done by the Austrian Foundry Research Institute. For all of the flexible materials, we have external fabrics, insulation, and bottom fabrics. We characterized the thermal properties from room temperature to almost the application temperature we expected for the mission. This was the characterization of the individual materials. In the second step, we designed a thermal contact experiment, or the colleague from the Austrian Institute designed that, which was focusing on the measurement of thermal resistances of the complete layup. Next slide. On the next slide, we see some photographs how that was done. We started with the layup was embedded inside a specially built mold. On the bottom, between the layers, we put thermocouples and some ceramic frame for insulation. Then we put or closed the mold at the top, and then a crucible filled with solidifying liquid copper was put on top in order to maintain an almost ideal temperature boundary condition there. This was taken for a specified period of 2 minutes, of 4 minutes, and then we took it away, and the measurements by the thermocouples were then put into a comparison with numerical rebuilding of the complete setup.
3-minute warning.
In the numerical modeling, we varied the thermal transmittances. And then we received some thermal resistance, which for this model very closely was to the insulation of the layups. So we could find out that the thermal transmittance or thermal resistances of the interfaces was negligible for the layups we considered. Next slide, please. Okay. That we went into arc heated facilities LBK, which has two tests like 2K and L3K, which have a long heritage in high entropy characterization and qualification of thermal protection systems. And we got for both missions a relevant chemical environment, because the L2K facility can easily be operated with a Martian mixture consisting of carbon dioxide with a bit of nitrogen added. Next slide, please.
1-minute warning.
Okay, so we had here, compared to the rigid TPS, we have the difficulty of having a sample holder which is appropriate to catch the flexible materials. We have here the possibility to take design from a former ESA study and could, for the stagnation test, and could adopt that to the tangential test as well. Next slide. For the test matrix, we considered, as mentioned, 2 test configurations, and for each test configuration, we had 2 test conditions, a maximum heat flux and a reduced heat flux, and 2 integral heat loads, a nominal from the trajectory and an extended heat load with 50% high, which was 50% higher. So in total, we had 12 tests per layup. Next slide. Here we can see some results from the Martian mission, and for layup 1 at the reduced heat flux. From the photographs at the bottom, you can see that we got a very uniform heating of the layup. From the plots, you can see that we got a very nearly steady state surface conditions. This is the left side plot, the black curves. And for the thermocouple measurements in the interior, we got a very good repeatability with a good insulation to the bottom, because the bottom temperature remains very low, just at the end of the longest test below 100 degrees C. Next slide. We have, one back. We have here some results from the tangential flow, now the Earth mission, and the observations were nearly identical to the stagnation tests. A good and nearly uniform heating with a slight temperature decrease in flow direction, a good steady state surface conditions, and a good repeatability with regard to the thermocouple measurements, and a low temperature increase at the bottom. This is the current status of the project, and with these results, next slide, next slide, please. We are going now to the analysis and adding at the end a second arc jet loop before we can go with the final modeling and go to define a future in-orbit demonstrator mission and the correlated system concept. Next slide. Thank you. I want to thank you all for your attention and be happy to answer some questions, maybe in the chat only.
Yeah, I think we're going to have to move on to the next talk. That was very interesting. Thank you, Burkhard. So please monitor the chat and answer any questions that come up there. And Tim, if we can have Hannah's presentation pulled up. So to close out the first half of the session, we're going to continue the theme of inflatable decelerators. And today, Hannah will describe heat flux gauge instrumentation development for the low Earth orbit flight test of inflatable decelerator project. Hannah received her PhD in aeronautics and astronautics from Stanford University, and she is currently working as a systems engineer for AMA Incorporated at NASA Ames Research Center in the Entry Systems and Vehicle Development branch. Please take it away, Hannah.
Hi, thanks. So today I'm going to tell you about what the LOFTED team has been working on in terms of calibrating heat flux gauges. So next slide, please. So LOFTED stands for the Low Earth Orbit Flight Test of an Inflatable Decelerator. So the LOFTED flight is a demonstration of a 6-meter hypersonic inflatable aerodynamic decelerator, or a HIAD. So as you all know by now, HIADs have many potential benefits over the rigid heat shields that we use today. So for rigid aeroshells, the size is constrained by the size of the launch vehicle's shroud, but inflatable heat shields, like the one on LOFTED, don't have that constraint. So since they can be bigger, they have the potential to enable the delivery of heavier payloads. So the LOFTED aeroshell is made up of 7 inflatable tori strapped together, like what's shown on the left, and then covered in a flexible TPS, which is that black material. And on the right, you can see a cross section. So you can see the 7 inflatable tori and then the center body with the rigid nose on top. And the LOFTED aeroshell is actually a secondary payload on a mission with an environmental satellite called JPSS-2. So after the satellite is released into orbit, the LOFTED aeroshell will separate and enter back into Earth's atmosphere, and then it'll land in the ocean. Next slide, please. So there's a whole suite of instrumentation that our team has been working on across the inflatable aeroshell, the rigid nose, and the center body. But today I'm going to be talking specifically about heat flux gauges. So that's both total heat flux gauges, which measure convective and radiative heat flux, and then also radiometers, which just measure radiative heat flux. The expected margined total heat flux for the mission is about 40 watts per centimeter squared. And the vast majority of that is convective, with just about 1 watt per centimeter squared expected to be radiative heat flux. So because of the expected environment, that led us to choose a total heat flux gauge with a range of 70 watts per centimeter squared, and a radiometer with a range of 3 watts per centimeter squared. And you can see the pictures of what they actually look like on the right there. And they're both Schmidt-Bolter gauges, and they have similar designs to those that flew as part of ERV-3 and Medley-2. And they're arranged on the rigid nose of the heat shield, with the total heat flux gauges positioned around the radiometer, which is in the center. And I also want to mention that, unlike most flights, Lofted is unique in having a minimum heat flux requirement. So since the goal is to test this new inflatable technology, we want to make sure that the materials are being adequately tested. So we want them to reach at least a certain heat flux. Next slide, please. So ideally, you'd be able to calibrate heat flux gauges in both convective and radiative environments, since heat flux gauges might respond differently to the two types of heat flux, which I'm going to talk about in more depth shortly. And also, for different missions, the amount of convective versus radiative heat flux can differ because it depends on the entry speed and the destination. So that ratio varies from mission to mission. But it turns out that there's actually no standardized way to measure convective heat flux because it's really difficult to know exactly how much heat flux is being applied, and it requires a pretty complex setup. But it is possible to apply radiative heat flux with a higher degree of certainty. And that's because radiative heat flux depends just on the material emissivity and the temperatures. So this is how most heat flux gauges are calibrated. And it's also the type of setup that we have at NASA Ames. So the setup at Ames, which you can see the picture of in the bottom there, has a range of 50 watts per centimeter squared. So that bounds our expected flight environment. And you can see at the top, there's a quartz lamp bank, so that shines the heat flux down onto a sled, and the sled can move back and forth. And so embedded in the sled is a reference sensor, which is a water-cooled guard-on gauge, and then also the unit under test sensor. And so the sled slides back and forth, and the light shines on the reference sensor, and then the sled slides over, and it shines onto the reference sensor. So then we can calibrate the sensor by shining different amounts of heat flux onto the sensors. So next slide, please. So as I touched on earlier, heat flux gauge calibration is notoriously difficult. So according to the literature, the response of a heat flux gauge to radiative heat flux versus convective heat flux can differ by over 20%. And then also, there was a study that calibrated the same sensors in multiple state-of-the-art facilities with just radiative heat flux. And the study found that the variation between facilities can be as high as 15%. And then within a single facility, the variation in response was found to be up to 3%. So initially, we planned to do all of our calibration at our vendor's facility. So we received the heat flux gauges from the vendor, and they had been calibrated there. But then we sent them back to be calibrated again because we wanted to see the repeatability there. And we saw changes in the calibration constant of up to 6%. So that's kind of what got us started at looking into this more, and eventually it led us to bring the calibration in-house to NASA Ames. And there are also a bunch of other sources of error that affect heat flux gauge calibration, which include mismatched material and thermal properties of the sensor and the substrate that it's mounted in, whether the sensor is mounted flush with the surface or if it's projecting outward, changes in surface properties due to handling, thermal contact resistance between the gauge and the substrate that it's in, so that can include air gaps and epoxy, and then also differences in the ambient temperature in which the gauge is tested, and also the surface temperature of the gauge itself. So next slide. So because of all of these uncertainties, as I mentioned, we brought the calibration in-house to NASA Ames because we thought that would give us more control over the process and a better understanding of what's going on. So for example, once we brought the process in-house, we were able to add temperature compensation to our calibration. So on the top right corner, you can see the sensor output, which is the blue line. So as more heat flux is being applied throughout the calibration, the output in millivolts is increasing. And this is just for one single calibration. And then the orange line shows the temperature of the gauge throughout that calibration. You can see that the temperature starts at about 30 degrees Celsius, but reaches about 140 degrees Celsius at the highest heat fluxes. And we realized that there actually is nonlinearity due to the changing temperature of the sensor. And so when we accounted for it, we were able to reduce the residuals between the fit and the data points from the calibration from about 2% to 0.5% of full scale. And so at least part of the reason for the temperature dependence is that the Seebeck coefficient for the constant copper coil in the heat flux gauge changes with temperature. And it's also likely that the thermal conductivity and the thermal expansion coefficient of the materials in the sensor are also temperature dependent. And then the other thing we wanted to do to buy down error was to calibrate the sensors in a convective heat flux facility. So the aerothermal response models of the flexible TPS were developed based on testing at the Large Core Arc Tunnel, or LCAT. And so we wanted to use that as an anchor for the heat flux gauge calibration. So even though we'd still expect to calibrate every heat flux gauge in the radiative facility at NASA Ames, we want to be able to map the calibration from Ames to LCAT to allow for better material response modeling, and eventually we'll be doing in-depth temperature estimates using the heat flux from flight. Next slide, please. So it wasn't really feasible to truly calibrate the heat flux gauges at LCAT, but we wanted to at least see how valid the radiative calibration would be in comparison to the convective calibration. So arc jets use slug calorimeters for the reference heat flux, but they still have significant uncertainty. So in the middle plot in the bottom with the green lines, you can see that the surface temperature increases over the course of the exposure from about 30 to 150 degrees Celsius. So this is one source of uncertainty. And then also, we suspect that there's some instability in the tunnel flow. So the red arrow there is pointing to a spot where the output seems to just step down suddenly by about 1 watt per centimeter squared. So when all was said and done, the convective calibration resulted in a difference in sensitivity from the radiative calibration by 3% and 9% for the two heat flux gauges that were tested. So on the right are some plots of showing the calibration. And so the orange points are from the radiative calibration. So you can see that they're very tight and it's a very tight linear fit. But the blue points are from LCAT, and so it's way noisier than the radiative calibration. So we definitely need a lot more data to feel more certain about relating the convective to the radiative calibration. Next slide, please. So finally, we have some future work planned and recommendations to buy down some of the sources of error in heat flux gauge calibration, which we think are applicable to a variety of missions. So we plan to expand the heat flux gauge characterization at LCAT to help reduce that 20+% uncertainty that we know results from differences between radiative and convective heat flux. And then also to address this, we want to explore the development of our own convective calibration facility at NASA. So we know that convective calibration has a bunch of issues and it's also really expensive, so that kind of motivates us into looking into developing our own. We're also interested in designing a temperature-dependent test setup. So the preliminary temperature compensated calibration that we did, as I mentioned, resulted in a pretty substantial reduction in error. And temperatures in flight can be even lower than what we tested at. So focusing on low temperature calibration would be really important. And then finally, there are also a number of other factors that affect the analysis of flight data. So making sure to consider those would continue to reduce uncertainty in heat flux gauge measurements. one example is to characterize the effect of deposition products on heat flux gauges. So even though we don't really expect this to be an issue for lofted because there won't be ablation, future high-ed missions and many NASA missions have ablative TPS material, so it's obviously very applicable. And then just some recommendations going forward that we've thought of. The first one is to consider multiple sensors to use as reference gauges in radiative calibration, since we really want to be able to know exactly how much heat flux we're applying during calibration. A second one is to incorporate temperature compensation into calibration, because as I mentioned, that can certainly reduce the uncertainty. A third recommendation is to test sensors in the same facility or environment in which the material response models were developed. So since we know that there's up to a 15% variation between facilities, this can at least give you internal consistency within the project. And then finally, we hope to continue digging into heat flux gauge uncertainty to enable better measurements for future missions. And we think that this is something that missions all across NASA could really benefit from. So thanks.
Thank you, Hannah. I think we have time for a few quick questions, Tom, if there are any in the chat.
There are not currently any in the chat.
Okay. Does anyone else have any questions out there that they want to
Michelle just dropped one. Hannah, are you collaborating with the Medley 2 team to learn anything from their HFG?
Yes, definitely. The heat flux gauges that are being used on lofted are very similar to the ones that were used on Medley 2. So I know Medley 2 is doing a lot of good work on looking at the effects of deposition and doing arc jet tests. So yeah, we're definitely working with them to learn from their experience.
Excellent. Well, I don't see any more questions, so thank you, Hannah, and to all the speakers for presenting their talks today. We are now entering a break that will last until 1/4 the next hour, and then at the bottom of the next hour, we will begin the second half oral presentation. So please join us for the second half presentations and the Q&A for posters. Thank you, everyone.
Hey there, Tom. Do we have you online for moderating the poster Q&A?
I am here, yeah.
Do we have someone from the poster conveners that are going to kick off the poster Q&A, or do we go right into it?
I think they will post the questions as they go on.
Yep, we can kick it off right now. Do we have any questions for our first poster?
All right, so this is to catch the name here. To Mr. Banerjee. So what do you think are the practical limits on the size of the microstructures imposed by using the ray tracing approximation?
So over here in the ray tracing approximation, whenever we are using microstructures, we have to make sure that we use a representative elementary volume. What that means is, let's say your initial microstructure is 200 micron, right? And you generate a set of optical properties. And you have to make sure, like when you're increasing the size of your microstructures for 300, 400 microns, they should remain within 1% of each other. So that's like known as a representative elementary volume.
Thanks. Okay, for Olivia, so do you think that adding hyperspherical capabilities to some of the cameras might improve photogrammetry and or science return?
Yeah, that's a good question. I'm certainly not an expert on spectroscopy or spectral imaging, but I think that's something that would be interesting to look at for future SCALPS missions if we are to continue including this payload on future science suites on the moon or elsewhere.
Okay. Aaron Brandis, how is ESM funded and coordinated between centers?
So ESM is largely funded via STMD, or Space Technology Mission Directorate, and SMD, which is the Science Mission Directorate. And in terms of sort of collaborating between centers, it's sort of mostly run out of NASA Ames and NASA Langley. So we have sort of PIs and PMs, and we have the PM and PI is at Ames, and then the deputies we have at Langley. That's mostly how we sort of run the project.
Okay, thanks. For Brendan, what studies do you plan to do now that you have a neural network that looks to match the experimental results?
So one thing about my research, the results that I have there are actually just preliminary and like a proof of concept. So I'm still actually in the process of building like the finalized neural networks. But once I have that finished and built and I've got all the parameters optimized, I'm just going to first confirm that I can like reproduce the current permeability results that I have, more or less. Except now, with rather than doing it by simulation, I can just simply put the parameters into the neural network, which is much more efficient, both computationally and just much quicker.
Okay, thanks. For Tyler, what type of jump conditions are fulfilled at implicit liquid-gas interfaces modeled by the level set? Is your code open source?
Yes. Hi, Julia. Thanks for that question. The code that I'm using is not currently open source. It's this multi-phase framework that we're building is being implemented in a code in-house at university in collaboration between University of Kentucky and University of Maryland. As far as the jump conditions, what we're using is what's called the ghost fluid method, and what it enforces at the interface is three properties. the pressure and the velocity are coupled, meaning essentially they're continuous across the interface, which is a standard boundary condition that you would expect, say, between a solid and a liquid, for example. And then, as we know, we have to close the Navier-Stokes equations, the Euler equations in this simple case. So there's one final property that we have to use, and in my framework, that's entropy. So we couple velocity and pressure, and entropy is essentially extrapolated. And that's how you couple the two sides of the interface and can run a multi-phase system.
Okay, thanks. Brendan again, how well does SVR support vector regression perform when predicting the permeability of materials that are outside the training data set?
So actually, those results presented in that poster presentation are for data samples outside of the training set. And for most of those results, the accuracy was actually within 10% of the experimentally predicted values. Also, those are for relatively low number of samples. I think only 173 samples. So we can expect the accuracy to improve as the number of samples increases.
Okay, for you as well, how does your approach handle time-varying permeability?
As of right now, it does not. So, yeah, that's the simple answer to that.
Okay. Aaron, non-equilibrium CN radiation plays an important role in the case of Titan. Venus is carbon dioxide, nitrogen atmosphere. Do you expect CN to play a significant role there too?
Not really. I mean, in the case of the Venus, the atmospheric velocity at entry is so much higher than at Titan that most of the molecules have been dissociated by the time we have the radiative heat flux. So the radiative heat flux at Venus is dominated by carbon atomic radiation in the vacuum ultraviolet.
Okay, Brendan, let's say you have near perfect accuracy. What becomes enabled by your faster analysis?
Right. So actually, with the perfectly trained neural network, we'll be able to solve much more complex problems. So, like specifically in our case, the simulations are done for a digital mesh of the TPS material. And so, one advantage that we have with the neural network rather than using through simulation is most simulations we have to summarize the mesh as a single value, such as like porosity or sample density or permeability. Whereas when feeding it into a neural network, we can actually feed in the mesh itself. And so into a convolution neural network, and then from the convolution into linear regression or whatever. And in doing that, we hope that we'll have a much more robust solution with the actual geometric data of the mesh itself, rather than just some average value like porosity or sample density.
Okay, thanks. Olivia, why do all 4 plume craters need to be imaged? Are asymmetries important for your task goals?
Yeah, that's a great question. So we do, I guess the most simple answer to that question is the more data we can obtain of these interactions, the better, just because it's something that we really want to understand well. And there's also a chance that depending on how the vehicle descends, it may not be firing all 4 pairs simultaneously, or perhaps different thrust levels might be employed. But this is also something that's sort of been a trade that we've done as this project has continued on, because as I kind of alluded to in my poster, you start to sacrifice accuracy the more of a wide view you try to take of these craters. So, and with our long focal length descent cameras, we had to kind of narrow down to one specific pair because otherwise we just won't be able to get accurate photogrammetry results.
Thanks. Question for Peter. How does your work relate to the plume surface interaction effort Ashley Corzin briefed us on during the last session?
It is directly related to that. The effort that Ashley presented includes an experimental component, a predictive simulation tool development component, and some instrumentation component. And the poster I presented is the predictive simulation capability development. So the experiments performed under that project will directly support our validation and improvement of the tools shown in the poster. So it is directly related.
Okay, Peter, again, has this code been applied yet to the Mars 2020 downcam videos of the descent plume?
There have been some discussions in that direction. We don't have direct funding to do that yet, but that is a distinct possibility, and it would be directly applicable. So yes, we're planning to do that if given a chance.
All right, we've got a couple more minutes. Any further questions? Oh, here we go for Giuseppe. So can you summarize the differences between the breadboard and the Draymond Strat? Draymond Strat or operational mode? Oh, I know. Giuseppe, are you there? He is on. Giuseppe, if you're speaking, we can't hear you. Perhaps you could respond in the chat. All right, we got time for maybe one more question. Anything else from anyone? All right. Well, Aaron, you want to take the ball back and start the next set of oral talks?
Yeah, happy to do it. Thanks a lot, Tom. Can you hear me okay?
Yep.
Great. Okay, thanks. Thank you very much to all of our poster presenters, and thanks for folks asking questions and engaging with those folks. And thanks to my co-conveners for all the work that they've done leading up to this. I think we had a good first half of the session, so let's get right into the second half. Very similar to the morning, I'll be keeping time, and I'll give you a 3-minute warning and a 1-minute warning. So without further ado, let me introduce our first speaker of the second half. We have Aaron Brandis. Dr. Brandis is a senior research scientist employed by AMA in the aerothermodynamics branch at NASA Ames. He's the DREAM PI, Dragonfly Aerothermal Lead, and PI for NASA's Entry Systems Modeling Project. His research focuses on shock layer radiation with the NEC-AIR code and EAST shock tube. Take it away, Aaron.
Great. Thanks for the introduction. So, hello, my name is Aaron Brandis, and I'm presenting on the Dragonfly Entry Aerosciences Measurement Suite, known as DREAM. So, as I just mentioned, I'm the DREAM lead investigator and work with a team of folks from NASA Ames and NASA Langley, DLR in Germany, Lockheed Martin, and APL, who are leading the Dragonfly mission proper. So you can think of DREAM as something almost equivalent to what Medley 2 was for Mars 2020. Mars 2020 included instrumentation on the heat shield and for the first time on the back shell as part of Medley 2. The team is still processing and simulating that data, but the first returns look great, as was shown at the IPPW Mars session a couple of weeks ago. So DREAM is an instrumentation suite embedded in the thermal protection system around the aeroshell to provide data about the aerothermal and aerodynamic environment during the Dragonfly entry at Titan. So DREAM is the first ESI, or Engineering Science Investigation, from a competed Discovery New Frontiers class mission as part of Dragonfly. So it's really, really cool stuff. Next slide. So what sensor packages make up the DREAM instrumentation suite? So similar to the MISP TC plugs on the Medleys, we have the Dragonfly sensors for thermal reconstruction, also known as Dragster. And so these thermocouples will be embedded into the peaker on the forebody and SLA on the back shell. And the two main goals for this data will be to reconstruct the aerothermal environment and understand the material response of the TPS. And similar to the MEADS transducers on the Medleys, the Dragonfly atmospheric flight transducers, or draft, will measure the surface pressure on the heat shield, which will allow us to understand the state of the flow near the TPS surface, as well as looking to better understand the dynamics and orientation of the vehicle. And then we also have the combined sensor system for Titan atmosphere, also known as COSTA, which doesn't have a Medley heritage, but rather comes from the COMARS sensor package that flew on ESA's Schiaparelli mission and will be provided by DLR in Germany. There will be 3 of these sensors on the back shell to measure pressure and radiative and total heat flux, and predominantly really focusing on understanding the radiation from the molecule CN. So DLR is also providing the data acquisition system for all of these DREAM instruments, and so are really a very valuable partner on this project. Next slide. So now to just touch on the goals for DREAM at a high level. So we are hoping to measure the near surface and in-depth temperatures in the TPS, measure pressure at the heat shield surface and on the TPS, the aft TPS, measure aft radiative and total heat flux. So being a New Frontiers mission, we have to work with certain constraints, such as a smaller budget as compared to the Medleys, and reduced data that we're able to send back to Earth from Titan as say compared to Mars. And of course, the most important thing for DREAM is to do no harm to the Dragonfly mission and its primary science objectives, as well as just really minimal interference as possible to mission operations. So really the solution we come to for this for DREAM is to use heritage flight-proven systems and by partnering with DLR. And also I thought it'd be worth mentioning this is really the first ever data set of this sort at Titan. And also it's interesting to note that it's the first in a non-oxidizing environment, which really means that we think we'll have minimal to even really no recession during the Titan entry. Next slide. So this chart just shows the aerothermal environment for Dragonfly, and they're really of a similar order of heat flux compared to the values either MSL or Mars 2020 designed to. The backshell heating is dominated by radiation and is higher than what was experienced during Mars 2020. But we're confident that heat fluxes are within accepted limits of our chosen TPS materials. So in this particular plot, the primary y-axis has the margin heat flux, and the secondary y-axis has the margin heat load against entry time on the x-axis. So we have the blue lines showing the convective heating, radiation is in red, and then the total is represented by the black lines. So just for reference, we're getting up to about 250 watts per meter squared margin total heat flux at the stagnation point, and this goes up to something like 300 watts per meter squared at the full body shoulder. And the heat flux is roughly equivalent in terms of the max heat flux, and with radiation contributing about roughly 1/3 of the total heat load. However, once we move around to the backshell shoulder, the radiation is really, really dominant and is up to about even as high as 90% of the heat flux, and that's around a total of about 55 watts per meter squared on the backshell shoulder. And this is the radiation that we're really trying to measure with the COSTA sensors, and specifically the radiation from the CN violet and CN red bands. Next slide. So here we can see our current preliminary list of DREAM science objectives. So what we really want to do is try and measure and understand the TPS response in a non-oxidizing environment, as this will be the first time we take measurements like this with no oxygen in the atmosphere. We want to understand the four-body aerothermal environment, trying to back out the heat flux that the heat shield experiences. We won't be able to take direct measurements of recession, but we will be able to tell if we get excessive recession by just seeing if the nearest to the surface thermocouple burns out. But because, as I mentioned earlier, there's no oxygen in the environment, we really expect the recession to be very negligible, if not zero. We will also be looking to measure the aft body radiative heating and its impact on TPS design. So we want to take measurements of the total radiative heat flux as well as the radiative heat flux from the narrowband radiometers. And as sort of alluded to earlier, they'll be specifically measuring the emission from both CN violet and CN red. We also want to understand the composition of the Titan upper atmosphere, as it's really important to back out what the free stream mass fraction of methane is. This mass fraction of methane really drives radiative heat flux and is, roughly speaking, directly proportional and linear across our sort of estimates of uncertainty in that mass fraction. We would like to understand when and how the heat shield transitions away from laminar flow, and we know that from the medleys that this happens to both MSL and Mars 2020, and we're a similar sized heat shield with tile Pika, so we do expect the flow to transition to turbulent flow here as well. And then given that we have up to roughly 2 hours to descend through cryogenic nitrogen, understanding convective cooling and what sort of relief this can provide the boiling temperature is another important effect, and it's something that's very unique to this entry at Titan. Next slide. So this slide gives a couple of examples of our preliminary level 1 science requirements. Just not all of them, just a few to fit on the slide that we're currently carrying for DREAM. And these map pretty well to the science objectives I just showed on the previous slide. So for each level 1 requirement, I'm showing a corresponding measurement that we'd make in the red text. So the first level 1 requirement I have here is to determine the aeroheating and reconstruct the aerothermal environment during the atmospheric entry phase. And we can infer this by just measuring the near and in-depth TCs on the heat shield. We're also going to evaluate if and when the flow transitions away from being laminar. So this would really require multiple plugs with near-surface TCs across the acreage of the heat shield. And from just these two requirements, you can sort of see that we can have competing science requirements. As for the flow transition requirement, you might want to have more TC plugs across the acreage of the heat shield, while for the aerothermal heating environment, you're more interested in having more thermocouples in an individual plug. We would like to determine the impact of thermal soak into the heat shield and better understand convective cooling. And then we also need to back out the composition of the upper atmosphere in terms of the methane concentration. And as I already mentioned, this is very important for evaluating and reconstructing the data when we get it back from Titan. We want to measure the heat fluxes experienced on the aft body of the vehicle during the entry phase, and we can get at this with the broadband radiometer, narrowband radiometers, and the total heat flux gauges, as well as the thermocouples. And then we also want to determine the area force coefficients during this roughly 2-hour descent into Titan, and we can measure this with the pressure transducers, both on the forebody and aft body. Next slide. So, really partnering with DLR is really an enabling aspect of DREAM and allows us to do so much more science than we would have otherwise. DLR had previously developed the COMAR sensor for the back shell of the Schiaparelli mission, and even though Schiaparelli had something of a hard landing on Mars, these sensors successfully measured heat flux, both total and radiative, and really confirmed for the first time the importance of radiative heating from midwave infrared CO2 at Mars. So DLR is developing the COMAR sensors for DREAM, which will be known as COSTA. And as a co-investigator on DREAM, they really are equally invested as we are to receive and analyze the data. And this makes for a much more productive collaboration than just procuring off-the-shelf sort of instrumentation. And DLR is also providing the data acquisition system for all of the DREAM instrumentation, which really consists of 3 boxes, 1 central processing unit, and then 1 unit for the forebody instrumentation, and then 1 other unit for the backshell instrumentation. And here we just have a couple of figures of the DLR instrumentation that was used for XMRs. We have the electronics box, the broadband radiometer. That in the case of XMRs is really focused on measuring from radiation from CO2, and now for Dragonfly will be focused on measuring radiation from CN. And then the combined sensor that measures the total heat flux and radiation, and then the pressure measurement. Next slide. So actually my presentation at IPPW last time at Oxford was actually about analyzing the Schiaparelli data. And so I just sort of wanted to summarize that in one chart here. So this plot shows the total heat flux against time for the COMARS 2 flight data, which is shown in the yellow circles. The NASA code results are shown in both blue triangles and red crosses, and are really basically on top of the flight data. There's also analysis from the Ariane group, which backed out the heat flux from the thermocouples, which is shown in the black line, and we also get really good agreement with those results. And these results actually go back into the sort of RF blackout phase of the entry. So this chart really ultimately summarizes that the sensors worked very, very well and measured the radiation from CO2, even though we did miss out on some of that data not being able to return back to Earth due to the impact on the Martian surface. But considering we really matched the flight data very, very well, this gives us both really great confidence in our simulation tools and also the instrumentation that DLR did develop. Next slide.
3 minutes.
Okay, thank you. So this slide gives a potential layout for where the sensors might go around the aeroshell. Due to the number of channels we have available to us on the data acquisition system, we are limited to 24 data channels on the forebody and 24 channels on the back shell. So this leads us to having basically 10 heat shield thermocouples and 4 heat shield pressure transducers, and that sort of current arrangement shown on the slide, sort of indicating that we might have up to 5 thermocouple plugs. So we could have maybe 2 to 5 thermocouples in each plug. And then on the aft body, we have 2 TCs in 1 SLA plug. And then the 3 of the total heat flux, narrowband radiometer, and pressure combined sensors for Costa, and then the 1 radiometer on the back shell. So next slide. So today I will be more or less leaving you with a question about how we really reconstruct this dream data. As we know, we need to have better estimates for the atmospheric composition of the upper atmosphere of Titan, and in particular understanding the methane composition in the free stream. As I already talked about, the reconstruction is very sensitive to the amount of methane we have in the free stream, and it's important to rate of heat flux. And the uncertainty we currently have in methane at the altitudes of interest to us is sort of in the range of 0.9 to 2.2%. So the altitudes during the entry phase are shown on this plot on the right are about 500 to 180 kilometers with peak heat flux of something around 225 kilometer mark. So this plot shows the variation in a couple of different mass spectrometer measurements that were made by Cassini against altitude and showing the methane ratio. So from this plot, it's really clear that we need to find a better way of estimating this concentration of methane so we can, in order to analyze the dream data. So obviously we can't measure it directly in flight, but maybe we can infer the concentration or back it up from some of the measurements we make. In particular, I'm thinking of maybe making that inference from the narrowband radiometers. And this is something that we need to look at, and it will be an active area of research over the next really several years. And we have some time. We won't be getting this data back from Titan for about 15 years or so. So if there are any folks in the audience who think this might be an interesting problem combining uncertainty analysis, statistics, and aerothermal simulations, this might be a good research topic to undertake. So I think that's really all I have for today. So thanks for listening, and happy to take any questions folks might have.
I think we got time for a question. Tom?
One question real quick here. So despite the lag of recession, despite the lag of recession, I'm expecting outgassing from the surrounding CPS to contaminate the radiation environment. Phenolic-based CPS starts contaminating at 46 degrees C. How do you plan to investigate this process and mitigate it?
So we might look at having both sort of wide angle and narrow angle radiometers. The narrow view angle radiometer from ExoMars, because it was a sensing element at the bottom of a well with no window, there seemed to be very minimal impact due to any pyrolysis gases or ablation products impacting that measurement. If we had the large view angle radiometer that had a window, like they did for Medley 2, you get a much better idea of what the total heat flux is, because the narrow view angle doesn't really tell you heat flux. It's more of maybe an irradiance type or radiance measurement. So, one option might be to try and fly both a large view angle and a narrow view angle radiometer. But that's still very much in work.
Okay. And there's one more question in the chat for you, Aaron.
Great.
All right. Thank you very much, Aaron. Let me go ahead and introduce our next speaker while we're bringing up the slides here. So next we have Professor Manuel Dominguez Pumar. He's a professor at Barcelona Tech in Spain. He has participated in the REMS, TWINS, and META wind sensors for MSL, InSight, and Mars 2020, respectively. He works in the design of and fabrication of sensors and in the design of controls for sensor optimization. Go ahead, Manuel.
Well, thank you very much. The objective of this presentation is to show a smart algorithm for sensors working under what we have called quasi-constant state operation. And we will show examples as examples, meta-wind sensors in March 2020, and also the application of this approach to chemical gas sensors. This is the joint work of two institutions, the Astrobiology Center in Madrid and also us at UPC. Next slide, please. So we will be talking about wind sensors and also chemical sensors. Let's introduce a little bit thermal anemometry. The idea is that you introduce two solids inside the fluid from which you want to measure the wind velocity. In one of them, you will inject heat and you will measure temperature, or you will set the temperature and measure the power needed to keep this temperature constant. And the other one will be used as a temperature reference for the temperature of the fluid. Next slide, please. If we see the most simple approach is that you inject a constant power, and then the moment that you switch from a wind 0 to wind 1, there will be a transient in the temperature, and from the temperature, the instantaneous value of the temperature, you should be able to infer the wind velocity. The problem with this approach is that the thermal circuits can be quite slow, so that this is not the usual approach taken, unless the structure is minimal and you have a very quick time response. Next slide, please. The usual approach is trying to freeze out the state of the sensor, so that instead of, imagine that you only have a representative temperature in the system, you keep it constant, and the moment that you switch from a wind 0 to a wind 1, you have to increase the power from P0 to P1. If you are indeed controlling the state of the sensor, it means that this change must be extremely fast. Next slide, please. Then the problem with that approach is that in general it is not possible to control perfectly the complete state of the sensor, because, for example, if this is a thermal sensor, you will have temperature distributions and you are not controlling the temperature at all points. So what happens in reality is that you build a number of outputs of your sensor, and the strategy that you can follow is to implement several feedback loops from one to several, so that these outputs remain constant. In this graph, we're changing the sensor. Now we are working with chemical gas sensors based on metal oxides. These are chemical sensing layers, and the resistivity of the electrical resistivity of the sensing layer changes as a function of the gas to which the sensor is exposed. In the first half of this experiment, the sensor is being controlled, whereas in the second half, it is not controlled. In the second half, for example, the moment that the sensor is exposed to ethanol, the resistivity decreases, and when it goes back to synthetic air, it increases. Whereas in the control operation, the resistivity of the chemical layer is constant, and then the output of the system is now the control being applied, which is the middle graph. Next slide, please. This approach is obviously a little more complicated. So what's the point? Why do you want to use this approach? Because in general, it gives you a faster response. If we shift the response and we compare, we may see that the control operation, the response is faster. In this case, for example, the recovery time has been reduced by a factor of 5, from 200 seconds to less than 40 seconds. Next slide, please. So, is everything happy with these controls? Yes and no. It certainly can accelerate the system, but the problem is that you should set appropriate targets for the controls, and also depending on the changes in the environment, it may well happen that your controls saturate, and therefore you must design an algorithm that dynamically adapts the target points of the control so that you continue obtaining measurements under all conditions. Next slide, please. So let's go now back to the wind sensor. In the meta-wind sensor, there are two booms protruding from the mast of the Perseverance rover, and at each one of these two booms, there are several 2D transducers. In each one of these 2D transducers, you have 4 silicon dies that are suspended in 4-legged structures. The idea of these 4-legged structures is to isolate the silicon die from the supporting structure, and therefore these 4 silicon dies are kept at constant temperature. The moment that you increase the wind velocity, then the total power must increase, and the angle, the information of the local wind at that position of the 2D transducer is obtained. The angle is obtained from the powers at each one of the specific dies. Next slide, please. In here we see a picture of the wind sensor 2, or one of the deployable boom in the meta, and we may see, for example, 3 of these 2D transducers on the surface of the boom. So the problem with this sensor is that the 4 silicon dies in each one of the transducers is exposed to the air temperature in Mars, and the air temperature can well swing 70 degrees during the day. So you must design an algorithm that dynamically adapts the temperature of the silicon dies in order to obtain at all moments good measurements. Next slide, please. So this is the scheme of the design algorithm. There is a first state in which you take, there is a fifth die, as a matter of fact, in each one of these transducers. You take the temperature of this die as the initial point, and then you slowly increase the temperature until the control reaches a reasonable output. And this is done by switching between state 2 and 3. Once you have reached a reasonable level for the control, then you go to normal operation, and the idea is to remain there as long as possible. The only way to get out of this state is that either you saturate high or you saturate low, and therefore you adapt the temperature accordingly. And then there is another sixth state in which you optimize. If the outputs are very low for a long time, they are not saturating low, but they are kind of low, then you increase the temperature target so that the counts are not so low and you have a good signal-to-noise ratio. Next slide, please. In here, we are seeing an experiment with the MetaWin sensor in ADLO. This is the plot of one of the boards. At the bottom left, we see the raw data of the control of the temperature of the hot dies, but basically there is a step, a staircase at the very beginning. So that is the initial initialization of the algorithm. Before 200 seconds, the temperature stops. And this is the reason for that is that at the top left, you have the output counts of the controllers, and they are at a reasonable level, which is around 5,000. And this is a reasonable level, taking into account how this has been built. Now, there is a moment on which an ionizer is blown onto the sensor. This is around 200 seconds. And at that moment, there are saturations in the silicon dies. So what happens then is that the algorithm decreases the temperature. It remains there. At the end, the ionizer is switched off at around 800 seconds. And then you may see that the output counts come very low at around 500. This is a low value, so that the optimizer, the sixth state, goes in, and the target is again increased. The sequence of the states during the experiment is on the right. Next slide, please. If we look at a zoom of this previous experiment, we see that the moment that there are saturation events, the target temperatures are changed, and the control remains without saturation. That is very nice, but if the output of the system is the control itself, we see that each time that we change the target temperature, the controls are discontinuous. I mean, you are changing the temperature, and therefore, obviously, the power needed is changed. So you must devise a way in which there is a continuous estimator, so that the estimation of the win or the parameter that you are sensing does not depend on the particular setting point of the algorithm. Yes. Can you please next slide? And that is the way this has been achieved in March 2020. What goes into the win estimator that uses a lot of calibration is the thermal convection conductances. And these are obtained for each one of the dies from the temperature of the hot dies, the air temperature, and an estimation of the convection, the heat convection loss to the air. This estimator is indeed continuous and allows to avoid the discontinuities provoked by any change in the temperature. Next slide, please. So that is very nice, and you may think, okay, that's obviously it's a thermal system, but can this be applied to a chemical sensor, which is kind of nonlinear system and kind of very much different? The idea is that yes, in here we have one of the control loops that we have designed for chemical sensors. In this particular control, what we are keeping is constant the resistivity of the layer, measured at constant temperature. And to do this, we change the average temperature sensed by the layer. It has a lot of fast switching of temperature modulations. Next slide, please. So we introduced one of these sensors in a piglet farm, and we were forced. That was not our initial idea. That we were forced to implement the meta controls in order to obtain to work with the sensors under control. So in here, what we are seeing is the results of two sensors. The sensor number 2, the one at the bottom, is not controlled, so it's simply kept at constant temperature, and then we observe the chemical resistivity, the evolution of the chemical resistivity as a function of time. Now, the top two graphs are the sensor 1, which was controlled, and there is a thin line in the top graph, which is the chemical resistivity of the layer, instantaneous chemical resistivity, and the target set by the control. As you may see, they are all the time overlapped. During the experiment in the farm, we arranged several events. One which was no ventilation, there was no particular open doors or whatever. Forced ventilation, there was open doors and a fan going on. Natural ventilation, simply open doors, and again, no ventilation. So at the very beginning, no ventilation, the controls are, the control output is in the middle of the graph. You may see that there is no particular event. I mean, it's kind of a flat curve, and there are no saturations. At the moment that we go into forced ventilation, what happens is that the controls immediately saturate. So it is necessary to adapt the target values of the control. Once we stop the forced ventilation and we go into the natural ventilation and no ventilation regimes, again, we have several saturations, so that indeed it is necessary to change the target values of the control. So if we look now at the control output, the middle graph, and we see this, and we try to, okay, let's think about what would be the gas concentrations taking into account this signal, we have a problem, because there are a lot of discontinuities, and it is not evident how to build a useful signal. So that signal was a synthetic signal that we have to create, and this is the orange signal at the top graph. You may see that within this graph, from the target values and the instantaneous value of the control. From this synthetic signal is one which is continuous and is able to provide continuous information. Next slide, please. In here we see an example of the transitions down from high ventilation to no ventilation, and we may see that each time that the sensor, that the control saturates, there is a transition in the target temperatures, and this triggers a small spike on the orange signal, and this is due because at some point you are, the moment that you are not controlling, with the transition between one target and the other, you are not controlling, in there you miss some data points, but in the end you have a nice continuous signal in the orange, which is comparable in shape with the uncontrolled signal. Next slide, please. So, summarizing, the quasi-constant state operation in general accelerates the time response of sensors. At some points, it can divide the time response of the order of 100 by a factor 100. It depends on the inner math of the chemical models or the thermal models. In any case, in real environments, it is necessary to design an algorithm that dynamically adapts the target points, because otherwise, most likely, you will have saturations. And once you are adapting the target points, it is necessary to design a method in which a continuous estimation of the variables to sense is made. Thank you very much.
All right, we got time for one quick question. We don't see any.
All right, since we're not seeing any questions in the chat, if folks have questions, drop them in the chat. Thank you very much, Professor Kumar. So let's move on to our next presenter here. We have John Schmidt. He's a graduate research assistant pursuing a master's degree in mechanical engineering at University of Kentucky in Lexington, Kentucky, under Dr. Alexander Martin. He's a team lead for the Kentucky Reentry University Universal Payload System, or KRUPS. Take it away, John.
Thank you. Yeah, so like you said, today I'm going to be talking about the Kentucky Reentry Universal Payload System, or KRUPS, and more specifically, I'll be talking about design and testing for a reentry flight, which is currently underway. And so, yeah, my name is John Schmidt. And so in the slide below, you'll see the other names of other people that have contributed greatly to this flight. Next slide. So here's the overview of what CRUPS is. So CRUPS is a method to test thermal protection systems, or TPS, in a reentry environment. So this is important for, traveling to Mars or reentering Earth. And so CRUPS seeks to measure thermal data from varying depths within the TPS as reentry takes place. And we want to use these thermal measurements to validate aerothermodynamic CFD, as well as material response codes. And more specifically, we want to validate the CATS code, which is being developed at University of Kentucky. And so far, CRUPS has completed 4 suborbital flights. So shown on the figure below, from 2017 to 2019, we conducted 3 sounding rocket launches, as well as a high-altitude helium balloon launch. And so these 4 missions consisted of ejecting a capsule from a suborbital altitude and verifying various subsystems. And these have allowed us to get to the point where we can now conduct a reentry hypersonic mission, which is the current one. And this current mission is called the Kentucky Reentry Probe Experiment, or CRAPE. And that's shown as the 2021 mission on the slide below. Next slide. So the objectives for the CRAPE mission are to gather temperature measurements from the heat shields as reentry takes place. We, again, want to validate safety codes. And we also want to demonstrate the use of a relatively inexpensive system of conducting reentry experiments. So this can be valuable with the fact that ground tests can often not fully simulate hypersonic reentry flights. So shown in the figure below are the 3 CRAPE capsules, and I will then go into detail on the design on the next slide, please. So here's the capsule design. So the geometry of each capsule follows that of the Deep Space 2 mission, shown on the bottom left figure. And for this mission, we decided to go with 3 capsules to increase the chances of successful transmission of data. All 3 of these capsules are 11 inches in diameter, and the dimensions are shown in the bottom right figure. And the internals of this capsule are similar to the Reaver mission, which had a similar objective and used the Iridium satellite network, which we also are using. Next slide. So the capsule TPS can be broken into 2 main types. So 2 of the capsules are outfitted with the Space Shuttle Tile TPS, shown on the upper right figure. And the 3rd capsule is outfitted with an experimental TPS, shown on the bottom right figure. And the figure below shows the cross-section of both of these TPS systems. And as you can see, that there are surface and bond line thermocouples inserted at varying locations in the TPS. Next slide. So each capsule can be broken up into the following subsystems. So looking at the figure on the bottom right, we have an exploded view of one of the capsules. So the first part is called the cork afterbody. That's the uppermost part of that exploded view. One step down, we have a 3D printed nylon internal housing. So this consists of an upper and lower part, which together provide structural integrity to the capsule, as well as provide a mounting point for the electronics. The next subsystem is the electrical subsystem. This consists of the battery, which is used to power the flight computer. This computer is responsible for gathering measurements from the thermocouples and using the Iridium modem and antenna to transmit the measurements using the Iridium satellite network. The lowest most part is the heat shield, which is used to protect the capsules during reentry. Next slide. The final subsystem is the crate ejection mechanism, or CREM. And so These consist of aluminum shells which fully surround each capsule, completely enclosing them. And they act as Faraday cages which block unintentional radio frequencies from escaping the capsules and interfering with ISS communications. So that's a requirement for any payload visiting the ISS to have a RF inhibit. And so the figure below has, you can see the aluminum shells. Additionally, there are little black parts shown in there those are pull tabs which are used for activation. So once these are removed, the places the capsules from a 0 power state to a low power state. I'll talk about that more in the next slide. And then these CREM shells are fastened together with a pair of polycarbonate bolts, and so you can see the little extrusions in the figure below. That's where the bolts are inserted, and they fasten the shells together. And I'll talk about why we chose polycarbonate in the next slide. Next slide, please. So here's a mission overview for CRAPE. So all 3 capsules will be placed inside the CREM shell that I just showed and loaded inside the Cygnus vehicle. And this will be part of the NG-16 resupply mission coming up. So they will be launched and taken to the ISS. Once the resupply mission is completed, the ISS crew will then activate each capsule by removing the that pull tab that I just showed you, and this places the capsule from a 0 power state to a low power state. So, and at this state, it is not allowed to transmit. However, the flight computer is turned on, and then all 3 capsules are loaded inside the Cygnus vehicle. The vehicle then undocked from the ISS, and it begins to deorbit, and it breaks up at around 60 kilometers. At this point, the 3 capsules will be released into the atmosphere, and the heating of reentry will melt the polycarbonate bolts, which I alluded to earlier, and will allow the Faraday cages to be shed from the capsules, and the capsules will be allowed to re-enter the atmosphere without any blockage of radio frequencies, and they will fully activate at this point and begin transmitting data at around 20 kilometers and transmit continuously until splashdown. Next slide. So next I'll go over some highlight of some tests that were conducted on these capsules to get them ready for the launch. So first of all, we had a battery vibration test. So 9 batteries were sent from NASA to be used for this mission, and these were capacity cycles before and after vibration testing. They were then taken to Yokohama Industries in Kentucky, and the vibration profile was provided by NASA. As a result, no external damage occurred to the 9 batteries. This was verified through the inspection, and no internal damage occurred. This was verified through the capacity cycling done before and after the vibration testing. So the example of battery is shown on the bottom left figure. And the vibration setup was also shown. On this slide, we have the capsule vibration test. So once the capsules were fully assembled, they were taken to the NASA Marshall Space Flight Center in Huntsville, and they were placed inside foam, as shown in the bottom right. This foam mimicked the NG-16 launch environment, and they were placed in the vibration shaker shown below. The vibration profile was used, which simulated the NG-16 launch loads. As a result, no external damage occurred to the capsules and no internal damage. This was verified by the fact, can you go back one slide, please? Yeah, thanks. No, this was verified by the fact that the capsules performed the same before and after the vibration tests, and so this allowed us to conclude that the capsules would launch the NG-16 launch load. Next slide. Another test that was conducted at Marshall was the EMI test of the CREM. So EMI stands for electromagnetic interference, and so that in order to visit ISS, a inhibit is required to prevent any EMI from interfering with communications there, and so the empty crab shell was taken to marshals at their EMI test facility, and a transmitter was placed inside this cram shell, and this would simulate the capsule unintentionally transmitting data while at the ISS. The RF amounts were measured on the external side of the cram shell, and the setup of that is shown on the right figure. Next slide, please. As a result, no RF leaked. As a result, the RF leaking was much lower than the maximum allowable amount provided by NASA. So we can conclude.
2 minutes.
Okay, we can conclude that this would be our safety inhibit for unintentional RF. And so next slide. So in conclusion, all 3 capsules were constructed at UK for reentry flight. Several tests were conducted. I just highlighted a few, these capsules as well as subsystems, and the success of these tests allowed the capsules to be qualified for this mission to ISS, and so these capsules are scheduled to launch in early August, and shown below are the capsules in the flight configuration. And next slide. So I'd like to acknowledge the following awards as well as people for all the contributions to this project, and I'd like to thank you all for your time.
Okay, John, a couple of questions in the chat. So have you tested the radiation pattern of the GPS and iridium antenna with the back shell? Cork-based materials tend to scatter or have other negative effects around those bandwidth.
Yes, we have conducted many tests, and yeah, we've chosen the cork to be a RF transparent material. Also, that the 3D printed material is also RF transparent, so there's no interference that from the back shell of the capsules.
Okay, and also, have you tested or do you intend to test the Faraday cage ejection mechanism?
Yes, and that was shown in the previous slide.
All right. Any other questions for John? Oh, here we go. Where is the CG on those units?
Yeah, so the CG is, that's a good thing I didn't have time to get into. CG is, it's stipulated by the diameter. So the diameter was 11 inches, and the CG has to be located 44% of that distance from the nose of the capsule up into the capsule. So that's the envelope. It's 44% of the whatever diameter capsule you have. That's your envelope from the nose of the capsule to the internal portion of the capsule. So, and all 3 capsules were tested, center of gravity were tested, and they were found to be within that requirement. And this requirement allows the capsules to self-stabilize as they re-enter the atmosphere. And that was the center of gravity location was also one of the things we tested in the previous suborbital launches that I alluded to earlier.
That's all there is.
All right. Thank you very much, John. So next up, we have Raj Venkatapati. Raj is, well, first of all, thanks to Raj for stepping in at the last minute to fill an open slot here. So Raj is currently NASA's Senior Technologist for Entry Systems and also the Chief Technologist for Entry System and Technology Division at NASA Ames. He led the advanced TPS technology development that resulted in HEAT, ADEPT, and 3D MAT, and laid the foundation for the MSR TPS. He also played a critical role in preserving the PICA capability for NASA. And that's a good segue into his presentation, so I'll let him take it away and tell you about one of his current focus areas. Go ahead, Raj.
Thank you very much, and thank you for giving me the opportunity to step in and talk about a topic of interest to me at this time. I could have titled this talk many different ways. How to avoid penny wise and pound foolish to other things, but it is really to preserve the TPS capability that takes long and hard to develop. If we don't preserve it, what happens? That's the essence of this talk. I want to recognize my colleagues, Murray Stackpool, Matt Gash, Don Ellaby, and Jay Feldman, who have been working in this specific area of making the case for why we need to preserve. Thanks to them. Let's go to the next chart, please. So I just want to give a history a bit. We started going into space with Apollo safely and get humans back. And between 1960 and 1985, we have gone to Mars, we have gone to Venus, and we have put a probe into Jupiter. But if you look at those missions that happened in a very short period of time, that Apollo heat shield was unique. It couldn't be used for Mars. Viking had developed their own TPS material. And Apollo and Viking, the chart that's shown on the right-hand side shows in terms of heat flux and pressure, which are the defining quantities for, primarily defining quantities for selection of TPS. Compared to those two missions, Pioneer Venus was orders of magnitude higher in terms of both heat flux and pressure. So the material selected was carbon phenolic, and the same material was used for Galileo mission as well because of the extreme interheating. Around 1980, the focus changed from this to space shuttle. As a result, there was a gap years. These gap years between 85 and 95 or so, that kind of degraded our ability in terms of the capability that we had. So when Pathfinder came along, even SLA had to be reinvented. And then successively, the Stardust and Genesis mission required new TPS because of the mass fraction required. And then there were new inventions that helped. But the TPS gap that I show in the right-hand side plot, that clearly where the missions were going from the experience of Pioneer Venus and Galileo. These were missions to Saturn, to Venus, sample return missions, and so on and so forth. There was a big gap. In between 2000 and 2010, there have been lots of studies and white papers were submitted to the Decadal Survey identifying this gap in TPS capability that was mission limiting. And then NASA also conducted 2 workshops to assess whether we could recover the carbon phenolic capability, which, by the way, atrophied in 1986 when the rayon that is required for that heritage carbon phenolic, when that factory burnt out and there was no ability in the US to make that rayon anymore. Let's go to the next chart, please. So the Decadal Committee, recognizing all of these efforts, had 3 findings and recommendations, 3 actually. One, they recognized that the base of the thermal protection system in 2010-2012 time period was very fragile, and that even developing small changes, improvements to TPS required years of work. This is a result of MSL not able to use SLA, and we had to find PICA or MSL. That now today, PICA is a staple material that's being used today. And in addition, a third finding was the need for the low density TPS materials. So all these 3 findings from the Decadal had a big impact. Let's go to the next chart, please. So NASA, in response, funded 3 material entry system related activities, primarily as a result of those findings. 3D woven TPS, conformal TPS, which already started around 2008, 2009, that was continued as a further development, technology development, and then the ADAPT. I will only talk about the first 2, primarily focusing on heat. So SMD and STMD are the 2 main arms that collaborated at that time. They agreed for the heat development. And HEAT stands for Heat Shield for Extreme Energy Environment Technology. And STMD was responsible for the technology development, and SMD was responsible for the mission infusion. So STMD and SMD together, they agreed on the goals for the HEAT project. It was to reduce the heat shield mass for that gap that I showed in the previous chart by 30 to 40% compared to carbophenolic. And also, those missions that were being studied at the time, they wanted lower G-load missions during entry because of the sensitivity of science instrument. That meant that large heat load essentially translated to. So not only that you need to reduce the mass fraction for comparable missions compared to carbophenolic, you also have to enable these missions at much larger heat load. In addition, the heat shield has to be scalable. With these three things, primary goals, then HEAT's technology development maturation plan was also described by STMD, what we had to do. Let's go to the next chart, please. So HEAT project started in 2014 in earnest, and it was completed in 2019. And there are three charts that you see. Those are in the backup, and I have included in this package. You can take a look at them. That kind of describe what are the various things that the HEAT project did in order to meet all of those requirements. And the bottom chart on the left-hand side essentially compares for various missions. This is Venus, Saturn, Ice Giant, and sample return mission at much higher speed than Stardust or Genesis. For each of those cases, across a broad spectrum of conditions, HEAT would achieve between 40 and 50% mass reduction. In addition, we also showed that the HEAT is much more robust than carbophenolic that we had used before. In all of the testing that we have done, laser testing to very high pressure, moderate heat flux conditions, HEAT never failed, then we knew we can fail carbophenolic in those conditions. As a result, in addition to it, there was an independent review board that followed the progress of HEAT from the beginning all the way to the end. They then certified HEAT to be a TRL 6 for mission to be used. Science Mission Director, in the meantime, had offered HEAT as part of the announcement of opportunities, both on Discovery and New Frontiers all along the way. And this chart essentially comes from a presentation I gave last week. I didn't modify it. So it talks about VEXAG and Venus missions primarily. But HEAT is very applicable, and HEAT has been recognized as a critical need for Ice Giant missions. And as earlier mentioned, it is also today baseline for Mars sample return mission, a variant of HEAT, just a single layer. It's a dual layer material, 3D woven material. We have given enough talks in the past about HEAT. Let's go to the next chart, please. So you saw the HEAT was developed as a result of the atrophy of carbophenolic. Pika today is baselined on Dragonfly, on SRO, MSR SRO, as well as MSR EUV backshell. If you look at Pika, between 1995, when it was invented, and 2016, this raw material, the rayon that's required to make Pika, has vanished 3 times. It has to be replaced by different. Every time there's a new material, rayon replacement, you have to go through the whole certification, qualification, and so on and so forth to make sure that it behaves the same way. In 2016, NASA decided, or 2018, essentially the project started, decided that we should use a domestic replacement, and that the replacement should have a very large commercial base. And we did. When we started this project in 2018, funded by NASA, in 2019, FMI decided to discontinue the carbon fiber foam. Carbon fiber foam is the carbon brick that the rayon is used to make. The carbon brick is infused with phenolic. That's how you make Pika. The reason was that the market forces impacted their profitability. They decided that they're not going to make fiber foam anymore for commercial. This then put the Pika at risk. NASA then had to work with FMI, and today the capability is more optimized and moved to a location to make the material needed for NASA missions consolidated. and without which we would not have PICA, it would have impacted the missions. So this is another case where the material capability could vanish, and this is part of the challenge. Conformal PICA is something that we had focused on, we had developed in the past, and it is a much better alternate to PICA. But we discontinued that at TRL4, so it's in the background, so to say. That could be a very useful technology to be matured for aero capture missions that will come in the next decade. Let's go to the next chart. So this chart, I'm just going to very quickly summarize. There's only very few materials. 3D woven and PICA are NASA-invented materials. The others are ACC, SLA, AccuCell. These are all lower performance capability. And then you have CIRCA and CPICA that are not yet TRL6 for the kind of missions that we're talking about, but they're also at a lower TRL level, they could be matured. Good. So in terms of TPS, we have very few materials in hand. So let's go to the next chart, please. Thank you. So what is capability sustainment? That's the key of this talk. So let me take a minute or two on this chart. Why?
3 minutes.
How? Thank you. So the current NASA mission selection in SMD is a competitive process for most of the missions except for flagship. That means that when the AO comes out and when a competitive process sets in, there's not much resources or time. Then once the mission is selected, in a 5-year time period, you're flying the mission, you're taking off. So there's not a time or resources given to proposers. They don't have the ability. So especially for NASA developed materials, it becomes impossible if they vanish, if the atrophy has set in, if something has to be revived. So this is where risk for mission proposers are very high, especially given there's not too many alternates for the TPS I showed. That means that the process is unfair. And that's why we didn't see many mission selection in the decade of 1990 to 2010, primarily because you didn't have a TPS, really. You could say even the proposers understood that, but they were taking risk, and that was recognized. It becomes untenable and unfair, okay? So if you look at where are the capabilities that could vanish away, this is where the PI and mission proposing management organizations, they propose, and prime and integrators, they depend on subcontractors and suppliers, vendors, as well as NASA centers for the capability, even for verification. So this is part of this challenge is where are these risks that could come? So if you have a capability availability, if you want to assure that, that means that you really have to be active about it. If you don't do anything, you accept atrophy. That means that when the time comes for you either revive heritage or you develop alternate capabilities that you saw, SLA went through that a couple of times now, and HEAT is and PICA. Otherwise, you don't have a mission. That takes time and money. Whereas a better process is if you have frequent missions, which we don't in the field. So that means that you do a risk assessment, actively engage the community to understand where the risks might be and start to look at risk mitigation options. So that's what this is all about, is being aware of the risk and be prepared to address those risks. Those risk mitigation could be anywhere between looking at alternates to that was done for PICA to finding alternate replacement like conformal PICA for PICA or whatnot. Let's go to the next chart. So this is conclusion chart. Actually, some of my recommendation is we can't affect this decade missions have all been selected under the current, and we are impacting our sample return mission with the HEAT development and PICA with the Dragonfly and NSR SRO. But what I'm talking about is a decade from now, 2030 and 40. This is where if we don't preserve the material that are high technology, high TRL level, then we will repeat the same mistake. So this capability is not just material, it is the expertise, next generation of people training them. And there's risk all everywhere in an ecosystem that is TPS, and we need to be able to recognize and do that. So with that, I take any question and answers. There's the next chart that's just acknowledgement. There's a number of people that worked, and there are backup charts that give you some more information. I'm done. Thank you very much.
All right, Raj, there's one question in the chat for you, but I think we need to move to the last talk.
Great, thank you.
Yeah, thank you, Raj. Okay, let's go ahead and let me introduce our next speaker. So next we have Gregory Villar. So Gregory is having the time of his life working at the Jet Propulsion Laboratory. He discovered the world of entry, descent, and landing while testing operations for the Mars Science Laboratory. And after living on Mars time for several months with the rest of the Curiosity rover team, Gregory started to bug AltGen once a week for a new gig. And this ultimately led to him spending the last 8 years of his life with the Mars 2020 EDL family. Following the successful landing of the Perseverance rover, Gregory now spends his days trying to figure out how to manage his previous bosses as the supervisor for Enter, Descent, and Landing Systems and Advanced Technologies group at JPL. Take it away, Gregory.
All right. Thank you, Aaron, for that introduction, and hello, everyone, IPPW family. I am presenting this on behalf of Adam Nelson, who is kind of our main EDL systems engineer on the EDL cameras and the rest of the EDL camera team. And I just want to say that I had the pleasure of being Adam's roommate the week of landing, and that was particularly cool because Adam was one of the first people to see and process these videos and images throughout the weekend. And so it was just such a surreal and shivering experience to kind of see these things trickle in one camera at a time and just huddling over his monitor and doing it with the rest of the team. So I'm hoping that all of you can kind of get a glimpse of that experience through this presentation. So next slide, please. All right, an overview for those of you who do not know. On the left is a table of the cameras that we have on board, or we had on board. And starting at the very top, you can see that we had 3 parachute upload cameras at the top of the aeroshell. These were there. So at the top of the aeroshell, we had a descent stage download camera on the descent stage with a little bit higher resolution. And we had 2 cameras on the rover, a rover upload camera and a rover download camera, and also a microphone that was on the rover. But unfortunately, we didn't record any or didn't capture any recording of audio during the video. Could you go to the next slide, please? Okay, so one of the main themes in the development and implementation and integration and testing and operations of the cameras is this concept of do no harm. You know, it's kind of like this item that we just tacked onto the system and on kind of on a best effort basis, but we really wanted to make sure that it did not interfere or cause harm or risk to the heritage EDL architecture. And part of the way we did that is, if you look at the block diagram on the left, near the rover at the bottom, there's an item called the data storage unit. And eventually, all of the cameras routed to the data storage unit. And this data storage unit was responsible for receiving all of the data during EDL. And a key component to this is not having the data interface interact with the rest of the flight system. So all of the cameras were turned on per kind of switches at specific times. And as they turned on, they're sending data to this data storage unit. Such that when after landing, it was only then when we transferred the data from the data storage unit to the rover computers and then eventually radiated to the spacecraft. So in terms of operations, on the right side, you can see here, all right, I hope this audio is better. Thanks, Pat. So for the parachute upload camera, we basically operated that soon before deployment at a frame rate of 75 frames per second in order to capture kind of the dynamics of the parachute inflation. And at the same time, the microphone was turned on, and also the rover camera at 30 frames per second. Soon after parachute deployment, in order to capture the rest of the operations of the parachute, we bumped down, or we stepped down the frame rate to 30 frames per second. This is really just, because things aren't happening as quickly, and in order to kind of preserve the data bandwidth that we had. So we kept the parachute upload camera on until just before backshell separation, and that's because the camera live on the aeroshell, and it was going to separate, so we needed to cut those interfaces. But at that point, we also, during Skycrane, we turned on the FH download camera and the rover upload camera, so that both of them could have captured, or so both of them could capture the Skycrane maneuver and eventually fly away. So let's go to the next slide. For archiving, here are links to all of the YouTube videos for a camera if you're interested. But again, since we were able to experience this as a team in 2020, days after, looking at little bits and pieces here and there, I think it'd be nice for all of us to share this experience together as well. So why don't we go ahead and play this video? It's a compilation of all the cameras in sequential order here. I'm not sure if audio is going to be, but that's okay. As we're playing these videos, I guess I could just color commentate, but I think something really important to note, and it's probably obvious, but this is really on Mars, right? It's kind of hard to believe because they look so great, and working on EDL for the past 10 years, 2 years on Curiosity and 8 years on Perseverance, it's just so fulfilling to be able to see these images, and and same with all the people who worked on all these hardwares and all of these systems, right? It's just like you can now see your hardware on Mars, and just seeing the entire system work. I mean, it really speaks to the saying of a picture is worth 1,000 words. What you're seeing right now is the rover download camera. I just saw the feature separate just moments ago, and now we're coming down here. Let's move, I can look in the chat. Part of what I'll mention too is, when we were getting the images down and videos, it was kind of at low resolution at first, and even then they were mind-blowing, especially during the Skycrane. But as we got the higher resolution ones, it was just, I remember the team thinking, like, this can't be real, right? And it's just like, I mean, we've never even seen the Skycrane kind of work on Earth, right? Because we've never done that type of kind of end-to-end test on Earth. So to be able to see it work successfully on Mars and have the video to do that is just really, really astonishing. At this point, we just separated from the back shell, kind of doing our divert maneuver here. And eventually, as you can see, as we get close to the ground, you'll see the plume, kind of our engines kick up dirt from the ground. There we go. And now we approach Skycrane, which just, again, unbelievable. The feeling of seeing this just sends shivers through my body every single time. There it goes, our spaceship. I think Adam liked to say that, like, this kind of shows that, like, we were the aliens on Mars. Well, all right, thank you, Tim. If you can go back to the slide set, that'd be great. All right, next slide, please. All right, so some notable detections. Obviously, the cameras are great because it showed us, it kind of proved to us all the things that we expected to see. Things like the parachute inflation, seeing the motor push off the deployment bag and the deployment bag going out, parachute inflation, the dynamics afterwards, seeing things like the plume surface interactions on the ground. That's all really great. But the cameras were also useful because of things that we didn't expect to see. So if you go to the next slide, this, for example, the radome from the parachute lane. So at the center of the screen, you see kind of the deployment bag, and next to the deployment bag, there's a circular structure that is the parachute closeout cone lid, protects the parachute pack during entry, and the item circled in red is the radome, which is a piece of that lid, really protecting one of our telecom equipment. That came off unexpectedly, unexpectedly, and so we'll work on kind of improving that design in the future as necessary. If you go to the next slide, another thing that we saw here, so the ice deposits, you can see in the interior of the heat shield, there are these like white streaks of lines. We also saw this on Curiosity with the body camera. Those are actually good things. They're kind of, they have deposits on the heat shield because it's so cold during cruise. But then the item circled in red, around the heat shield there are 9 push-off springs, and this one actually kind of came loose. And watch the video, you can see this spring go from the outside of the heat shield all the way to the center as it goes down. The next question, please. Sorry, next slide. All right, so lessons learned for future imagers. Because part of, as I mentioned earlier, do no harm was kind of one aspect of implementing the EDL cameras onto our system. Another thing was we kind of got what we can get. We didn't want to interfere too much with kind of the schedule and all of the rest of the integration and testing of the spacecraft. So there were things that we could not do, right? Just like put the cameras on and you get what you get. And so here's some future lessons learned in order to help with things like reconstruction. First and foremost is generating kind of camera models. We did this with all the other cameras on spacecraft, but things like calibrating color and geometric values. And also it was kind of difficult that there wasn't really clock synchronization. So Adam and the team had to do that after the fact, kind of syncing up the images and timestamps with the different clocks that we have on board in order to help with video reconstruction. So hopefully we can do a better job doing that in the future. In terms of resolution, the download camera was great, but if we can improve that resolution such that we can get better imagery that would be better than high-res imagery at the altitude of backshell separation. And then for frame rates, of course, you can always use more frame rates for parachute inflation since all of that happens really, really quickly. But I think one of the most important things to realize from this is that these were very, very valuable, the EDL cameras. And I think all future missions should have things like the EDL cameras because we can kind of verify, the things that we expect to go the way they do, and also just capture things that we didn't expect to happen, like the radome, the parachute cover, and the push-off spring. Right? And these type of things we would not be able to see in other telemetry, just in kind of video images. So that would also help us kind of improve design in the future. And one last note here, Ashley presented last week, but now these videos will be able to assist with plume surface interaction studies that her and her team will do. Okay, last slide, please. I just want to leave on this note, and for those of you following, this is a really cool kind of encrypted message being created on the parachute. The internet solved it within hours of release, but I thought this was a fun fact that in addition to great engineering, it's a great way to kind of engage the public on the things that we all do, right? So the more we can do to get people excited, the better for all of us. So thank you, and I guess I could take some questions if we have time.
Yeah, we got time for a couple of questions here. So, or maybe just one. So first, has the reason for loss or non-acquisition of audio data during EDL been determined since some audio has been acquired post-landing? Was it commanding or configuration issues?
Yeah, I can't seem to remember if that was released information yet, but I mean, you're right. We did have audio recording from the EDL microphones post landing. So I just have to get back and see if that's actually released.
Okay. And one more here. I'm not aware of spaceflight qualified USB 3 cameras. Were you using commercial off-the-shelf cameras?
Yes, they were commercial off-the-shelf cameras that I did. While you guys close up, I could probably look up the published material and put it in the chat.
Okay. Thanks. That's all the questions in the chat.
Thanks, everyone.
Okay, thanks, Gregory, and thank you to all of the presenters from the second half and the first half. I'm going to turn it over to Julia, who is going to close this session out.
Hi, do you hear me okay?
Yeah, I can hear you, Julia.
Yeah, okay. Hi, so the successful 2021 EDL Technology, Science and Instrumentation session comes to an end. So on behalf of all EDL session conveners, we want to thank again all speakers and poster presenters for their exciting contributions. And in particular, I want to thank Michelle Monk, our accomplished keynote speaker, for delivering a great All Steve Award lecture to our session. And a special thank also goes to the chairs of the program organizing committee, Jill, Jörn, Som, and Todd, who made this year's virtual IPPW possible in the first place. Thank you also to the poster session coordinators, Manuel, Jacob, Clara, and Lynn. As this was the third of 6 IPPW sessions this summer, I take the opportunity to remind you about the upcoming IPPW session on innovative concepts for exploration. It's going to take place 1 week from now on Tuesday, July 27th. And don't forget to register separately for the session on the IPPW website. With that, and again, on behalf of all EDL session conveners, thanks for participating. Have a good day or evening, night, depending on where you are in the world. We are definitely looking forward to IPPW next year and having the chance to gather the community in person once again.